Hello there, and welcome to Science for Sleep, where curiosity gets comfortable and science drifts gently beside you. Tonight, as the world outside grows quiet and the last bits of daylight fade into the soft, star-scattered dark, we'll take a slow and steady journey to one of the most mysterious places ever found. Somewhere so far away that even light struggles to escape its pull. A place that exists not as an object, but as an absence so deep that it reshapes everything around it. It's called Holm 15a, and it holds something almost too massive to believe, a black hole that might just be the largest known in the universe. But before we fall into that cosmic depth together, I want to ask you something small and familiar. Where are you listening from tonight? Maybe you're in bed, your pillow cool, the sound of this voice filling a quiet room. Maybe you're lying on a couch with the glow of a lamp somewhere behind you. Or maybe you're watching the night sky through a window, wondering what those distant pinpoints really are. Wherever you are, this moment, right now, is part of something immense. The same universe that holds stars and galaxies and black holes also holds you right here, breathing in rhythm with it. If you find this slow kind of wonder relaxing, if you like the feeling of letting your thoughts drift through science like clouds moving across a night sky, I'd be ever so grateful if you gave this little space a like, maybe even subscribed. It helps more people find their way here. People who might need a calm voice and a reason to look up. And now that you're settled, let's begin this quiet journey. Because out there, buried in the center of a galaxy that lies hundreds of millions of light years away, is a black hole so heavy, so vast, that it defies even the imagination of the scientist who first measured it. Imagine a galaxy like a glowing island floating in an invisible sea. Billions of stars swirl together in patterns that take eons to change. In the center, as in most galaxies, there is something hidden, something that shapes everything else around it. Holm 15a is one of those galaxies. It sits inside a great cluster known as Abell 85, a vast community of galaxies bound together by gravity. If you were floating out there far beyond the Milky Way, you'd see Abell 85 as a faint shimmering patch of light, each galaxy just a fleck within a colossal structure. Holm 15a is one of the brightest members of that cluster, but it's not brightness that makes it special. It's what lies at its heart, something that bends the paths of stars and alters the dance of entire systems. When astronomers first began to study Holm 15a closely, they noticed something unusual. Its center wasn't behaving the way galactic centers usually do. Most galaxies have a dense, bright core, where stars cluster tightly under the pull of gravity, but Holm 15a's core looks strangely empty, a kind of hollow glow, as though something enormous had cleared it out. That empty look was the first clue that something extraordinary might be hiding there. Scientists began to measure the motions of stars near the center, tracking how fast they moved, how their light shifted as they orbited the invisible mass inside. These measurements, subtle flickers of light stretched or squeezed by movement, are the fingerprints of gravity. The stronger the gravity, the faster the stars move. As the data came in, the numbers began to make less and less sense. The speeds were far too high for the visible matter to account for. The central mass that was tugging on those stars had to be vast, beyond anything previously recorded. When they finally calculated it, the result seemed almost unreal. The black hole at the heart of Holm 15a was estimated to weigh about 40 billion times the mass of our Sun. 40 billion suns compressed into a single region from which not even light can escape. For comparison, the supermassive black hole at the center of our own Milky Way, called Sagittarius A1, has about 4 million solar masses. The difference is staggering. Holm 15a's black hole is about 10,000 times heavier, a scale so immense it's hard to even picture. To get a sense of it, imagine if our Sun were replaced by this black hole. Its event horizon, the boundary beyond which nothing returns, would stretch far past the orbit of Pluto, swallowing nearly the entire solar system. Every planet, every moon, Every comet would lie well within its gravitational shadow, yet from a distance it wouldn't look like anything at all. No bright flame, no shimmering surface, just a sphere of darkness surrounded by a faint halo of light, the last photons spiralling inward before they vanish. But the wonder isn't just in its size, it's in what that size tells us. Black holes like Holm 15As form through the merging of smaller galaxies and their central black holes over billions of years. Each time two galaxies collide, their stars mingle, their gases blend, and their black holes sink toward the centre, eventually joining into one. The larger the cluster, the more mergers, and the larger the resulting black hole can become. Holm 15A seems to be the result of countless such collisions, a cosmic matryoshka of devoured galaxies, each one adding its own dark heart to the growing core. Over time, the process left behind not just an enormous black hole, but a galaxy centre that's been swept almost clean of stars, like the calm at the centre of a storm. And yet, even with all our telescopes, we can't see the black hole itself. We only see what it does to the matter around it. We see the stars speeding through the void, the faint glow of gas being pulled inward, the subtle gravitational lensing as light bends around the unseen mass. It's like studying the wind by watching the motion of leaves. The thing itself remains invisible, but its touch is everywhere. The researchers who studied Holm 15A used some of the most powerful instruments available, including the Very Large Telescope in Chile. By mapping the way starlight shifted, they built a model of the galaxy's interior. Every data point, every pixel of that model told a piece of the same story. Something enormous was there, and nothing but a supermassive black hole could explain it. The discovery sent quiet ripples through the scientific community because it raised a question that still lingers. How does something that big exist so early in the universe's history? Even with billions of years of galactic collisions, the numbers didn't quite add up. According to current models, it shouldn't be possible for a black hole to grow that massive without violating the limits of known physics. Yet there it was, heavy and silent, a cosmic fact that refused to fit neatly into theory. You can almost imagine the scientists staring at their results late at night, monitors glowing in the dark, coffee cooling beside notebooks filled with equations, all of them wondering the same thing. Did they measure it right? Could something else mimic that kind of gravitational signature? But the evidence held. Independent analyses confirmed it. Holm 15A really did contain what looked like the most massive black hole ever found. The more they checked, the more convincing it became. Out there, nearly 700 million light-years away, sits a void that outweighs entire galaxies. If you could somehow hover above it and look down, you wouldn't see a clear edge or a defined shape. Instead, you'd see light twisting, stretched thin as it spiraled into darkness. You'd see stars whipped around by gravity so fierce that a second there might pass as an hour for you. And yet, to the black hole itself, time would stand still at the horizon. Every photon that crosses that line vanishes, its story ending where physics runs out of words. It's strange to think that something so destructive can also be so fundamental. Without black holes, galaxies might not form the way they do. They act as anchors, shaping the orbits of billions of stars, influencing the growth and structure of entire cosmic systems. Holm 15A's black hole isn't just a curiosity. It's a keystone in understanding how galaxies evolve. Every bit of data about it helps refine our models of the universe's architecture. And yet, there's still a sense of awe, a kind of reverent uncertainty, because for all we can measure, the truth of what happens inside remains unknowable. Even the word hole can be misleading. It suggests emptiness, but a black hole is anything but empty. It's a region of space so dense that gravity overcomes every other force. The matter inside is crushed to an infinitesimal point, a singularity where the known laws of physics break down. Around that singularity is the event horizon, the threshold beyond which escape becomes impossible. For Holm 15a, that horizon is vast enough to swallow solar systems whole. It's not a hole in space, it's space itself, distorted beyond recognition. If you could approach it safely, which of course you couldn't, you'd feel gravity increasing smoothly at first, then exponentially. Light would bend around you, time would stretch, and the view behind you would fade into darkness. The radiation near the horizon would be deadly, but the view would be breathtaking, an endless whirlpool of starlight spiraling toward oblivion. Yet from a comfortable distance, say millions of light years away, it's perfectly safe to imagine. And that's what we're doing now, letting our minds travel where our bodies can't, exploring the cosmos not with rockets but with curiosity. Sometimes lying in bed thinking about these things can be oddly comforting. The sheer scale of it puts everything into perspective. The small frustrations of the day, the unfinished tasks, the worries that hum quietly in the background, all of them shrink beside something like Holm 15a. It's not about feeling insignificant, it's about feeling part of something vast, a universe that holds both chaos and order, destruction and creation in the same breath. There's also a strange calm in knowing that black holes, for all their fearsome reputation, are essential to the balance of galaxies. They regulate star formation, shape orbits, and recycle energy through their gravitational influence. Without them, the universe would look very different, perhaps less structured, perhaps less beautiful. Holm 15a is a kind of cosmic elder, a remnant of countless galactic lives that came before. Its mass is a history book written in gravity, a record of every merger, every swallowed star, every pulse of light that never escaped. If you could listen to it, not with ears but with instruments sensitive enough to catch the vibrations of space-time itself, you might hear a low hum, a gravitational echo rippling through the cluster around it. These waves are too faint for human senses, but they travel across the cosmos, reminders that even silence has structure. When two black holes merge, they send out ripples that carry energy across billions of light years. Somewhere, Holm 15a may have once produced such waves, the deep cosmic equivalent of a whisper that never ends. And as we think about that, it's easy to forget how new all this knowledge is. Barely a century ago, black holes were just a mathematical idea, a strange prediction of Einstein's equations. For decades, many scientists doubted they could exist at all. Now we've photographed one, listened to the sound of another merging, and measured one that defies comprehension. Every discovery reshapes how we think about the universe, and Holm 15a stands at the edge of that understanding, challenging us to look deeper. So here we are, drifting together through thought, from the quiet of your room to a galaxy so far away that the light leaving it tonight won't reach us for hundreds of millions of years. Yet through science we can touch it. Not physically, but intellectually, emotionally, maybe even spiritually. It's a reminder that knowledge itself is a kind of bridge, connecting us across impossible distances. Somewhere, in the black heart of Holm 15a, space and time twist together in silence, and that silence, strange as it sounds, has brought us closer to understanding everything else. When you think about something that doesn't let light escape, it's natural to imagine emptiness, but the black hole in Holm 15a isn't just a hole in space. It's more like a shadow cast by gravity itself, a region so dense that even the universe seems to hesitate around it. What we call darkness here is really the absence of any signal, a silence so complete that it feels alive. And yet, through that silence, astronomers have learned to listen. They've built instruments that can see what the human eye cannot, tools that read the faint radiation and the distorted glow of stars circling an unseen center. From that light, from those invisible motions, they begin to draw the outline of something too large to ever truly see. Holm 15a is about 700 million light-years away, a distance so extreme that the light we detect today began its journey before mammals walked the Earth. The photons that now reach our telescopes left that galaxy, when our planet's continents were in different places, when life itself looked utterly different. Each flicker of light carries not just data, but history, a record of what was happening long before we existed to measure it. That light, faint and stretched by the expansion of the universe, whispers of the structure it left behind, a galaxy more massive than our own, with a heart that defies the ordinary behaviour of matter. Astronomers often start by measuring brightness to infer a galaxy's mass. The more stars it contains, the brighter it glows. But when they compared Holm 15A's brightness with its gravitational influence, the numbers didn't match. The galaxy wasn't nearly bright enough to account for the pull it exerted on surrounding stars. There was a missing component, something adding mass without adding light. It wasn't dark matter in this case, though the universe is filled with that invisible substance, but something even more concentrated. A single, staggering object at the core, distorting everything around it. The team that first made the measurement used a method called stellar dynamics. It involves tracking the way stars move near a galaxy's centre. Those motions tell you how much mass must be present to keep them in orbit. In Holm 15A, the stars near the core were moving at astonishing speeds, some over 1,000 kilometers per second. To keep them from flying away entirely, there had to be a gravitational anchor of extraordinary power, and that meant a black hole of unprecedented size. When the numbers came out, the result was almost unbelievable. Around 40 billion solar masses. That's not an exaggeration. It's a number that makes even the most seasoned astronomers pause. To understand what that really means, imagine stacking suns, 40 billion of them, each one 1,000,000 times larger than Earth. Now imagine compressing that unimaginable total into a sphere where gravity is so strong that not even light can climb out. The boundary of this region, the event horizon, would stretch across a distance of about 800 astronomical units, which is roughly 20 times the distance from the Sun to Pluto. It's an object so vast that if you replace the Sun with it, every planet in our solar system, and then some, would orbit within its darkness. Yet from hundreds of millions of light years away, it's just a faint gravitational echo, a ripple in starlight that hints at something too large for light itself. Black holes like this one are called ultra-massive black holes. Even among the giants of the cosmos, they stand apart. Most supermassive black holes at galactic centres weigh between a few million and a few billion suns. Holm 15A's is in a class of its own, the upper limit of what we've ever detected. There are theories suggesting that such enormous objects might form when several large galaxies merge repeatedly, each bringing its own black hole to the centre. Over time, those black holes spiral inward, drawn together by gravity and by the drag of surrounding matter, until they finally merge into one. Each collision releases gravitational waves, invisible ripples that carry energy away and allow the new black hole to settle into stability. Holm 15A in this picture is the end result of countless such unions, a monument to the cosmic history of collisions. But there's another way to think about it. Instead of seeing Holm 15A's black hole as the end of something, you could see it as a beginning, a structure still growing, still feeding on the matter around it. In the dense environment of a galaxy cluster like Abell 85, galaxies don't live in isolation. They move through the cluster's gravitational field like boats on a shared ocean, sometimes colliding, sometimes passing close enough to strip gas and stars from one another. Over billions of years, that process funnels material toward the centre, where the largest galaxy sits. Holm 15A is that central galaxy, and its black hole is the ultimate collector, slowly pulling in the energy and matter that drift too close. From our perspective, it's silent and still, but up close, the environment around it would be anything but quiet. The accretion disk, the swirling cloud of gas and dust heated to millions of degrees, would glow in X-rays and ultraviolet light. Magnetic fields would twist the plasma into spiraling jets that shoot out for thousands of light years, thin beams of radiation that could light up half a galaxy. These jets are how black holes announce themselves. They turn gravitational energy into motion, into visible light, into shock waves that sculpt the surrounding space. If you could somehow stand in the outskirts of Holm 15A's galaxy and look toward its center with X-ray vision, you'd see that thin, bright lance of energy piercing the darkness, a signature of a black hole at work. Yet even that light is only a faint trace compared to the mass hidden within. The paradox of a black hole this big is that it can be both the brightest and the darkest object in a galaxy. The matter falling towards it releases enormous energy, but the hole itself emits nothing. What we see is the struggle between gravity and radiation, a perpetual tug of war at the edge of visibility. Scientists model this using equations that balance infall and outflow, the rate at which matter is swallowed versus the rate at which it escapes in jets. For Holm 15A, the data suggests a black hole that is both stable and ancient, having reached a size where its feeding has slowed to a steady, almost serene pace. It no longer devours at the frantic rate of a young growing galaxy. Instead, it maintains a quiet dominance, shaping the galaxy around it with the weight of its presence alone. One of the most fascinating aspects of studying black holes this large is that they push the boundaries of our theories. The equations that describe gravity, Einstein's general relativity, work beautifully for most situations. But as we approach extremes like Holm 15A's core, those equations begin to strain. The densities become so high, the curvatures of space so intense, that even the best mathematics we have starts to lose clarity. Some physicists suggest that inside such a massive black hole, new physics might emerge. Perhaps clues about how gravity connects to quantum mechanics, the theory that governs the tiniest scales. These are questions that can't yet be answered, but Holm 15A reminds us that the universe is still full of unsolved mysteries. Astronomers sometimes describe these enormous black holes as fossils of the early universe. That's because to reach such size, they must have begun growing very early, only a few 100 million years after the Big Bang. The seeds of these giants might have been massive clouds of primordial gas that collapsed directly into black holes, bypassing the stage of star formation entirely. Those early seeds, perhaps tens of thousands of solar masses, then fed on surrounding matter, merging and expanding across cosmic time. By the age of the present-day universe, some had grown into monsters like the one in Holm 15A. Studying them helps scientists understand how structure emerged from the uniform fog of the early cosmos. There's also something deeply human about this search. Every telescope aimed at Holm 15A represents thousands of hours of design, construction, and cooperation across continents. Observing something 700 million light-years away is not just a technical feat, it's an act of imagination. We build instruments to extend our senses, to see what our eyes never could, and when the data returns, faint lines and tiny shifts in wavelength, we translate it into understanding. A small flicker of light becomes a clue about a force so immense it reshapes space itself. That's the quiet beauty of science. It lets us grasp the invisible. If you were to look at Holm 15A through an optical telescope, it would seem peaceful, just another bright elliptical galaxy surrounded by smaller companions. The danger and power hidden in its core would be invisible. That contrast between the serene appearance and the violent reality is part of what makes studying black holes so captivating. They remind us that the universe often hides its most extraordinary secrets behind unassuming faces. As the mind wanders through thoughts like these, it's easy to feel the pull of scale. We live on a small world orbiting a medium-sized star in an ordinary galaxy, and yet we can detect, calculate, and understand phenomena that dwarf every concept of scale we know. Holm 15A's black hole isn't just an object, it's a statement about what the universe is capable of creating. It's a reminder that gravity, the same force that keeps your feet on the floor, can also carve holes in the fabric of reality itself. The only difference is scale. The more we learn about these ultramassive black holes, the more they reshape our sense of cosmic proportion. They challenge the idea of limits, both physical and intellectual. A century ago, the idea of a 40 billion solar mass black hole would have sounded absurd. Now it's data, published, peer-reviewed, part of the known catalogue of the universe. Somewhere out there, beyond the reach of every photon we can collect, gravity has done something extraordinary, and we are just beginning to understand it. The shadow of Holm 15a is not simply a void. It's an expression of order hidden within chaos, a structure made from collapse, a paradox of creation through destruction. Every star it swallows becomes part of something larger. Every orbiting light curve adds to our knowledge. And as we continue to observe, refine and imagine, the picture sharpens, the story deepens, and the darkness becomes just a little more familiar. In the quiet of the night, as you lie listening, the thought of a black hole this enormous might sound unsettling, but there's comfort in it too. The universe is vast beyond measure, yet it obeys patterns, laws and rhythms that we can study and understand. Holm 15a is part of that pattern, a heavy, silent anchor in a sea of galaxies, moving to the same cosmic rhythm that we, in our small way, share. To understand the enormous black hole at the heart of Holm 15a, we have to understand the galaxy that shelters it, because galaxies and their central black holes evolve together. One cannot truly be described without the other. A galaxy is not just a collection of stars. It's a story written across billions of years, shaped by collisions, by mergers, by the slow pull of gravity that draws smaller systems into larger ones. Holm 15a is one of those galaxies that seems to carry the weight of countless ancestors, each absorbed over cosmic time until only this vast, luminous remnant remained. When astronomers describe Holm 15a, they call it an elliptical galaxy, the largest and brightest member of the Abell 85 cluster. Elliptical galaxies are different from the grand spirals most people picture when they imagine a galaxy. They don't have arms or elegant disks of dust and gas. Instead, they are more like glowing spheres or ovals, their stars distributed smoothly and evenly, without the structured patterns of younger galaxies. They are, in a sense, the retired giants of the universe, the end stage of galactic evolution. Spirals grow into ellipticals through mergers, and each collision smooths out the patterns, scattering stars until only the gentle gradient of light remains. Holm 15a is the ultimate example of that process, a cosmic elder surrounded by the remnants of smaller galaxies it has consumed. At its core lies a remarkable feature, a region astronomers call a depleted core. Most galaxies, even elliptical ones, have dense centers where stars crowd tightly together, shining brightly in the middle. Holm 15a, by contrast, has a faint, nearly hollow center. The brightness actually dips near the core, as though something has swept the stars aside. That hollow is one of the clues that led scientists to realize something extraordinary must sit within. When two galaxies merge, their black holes eventually fall to the center, orbiting one another as they spiral inward. As they do, they fling nearby stars outward through gravitational interactions, effectively clearing out the core. Over multiple mergers, this process repeats, deepening the hollow each time. By the time the final black holes merge, what's left is a vast, faintly glowing cavity, where once there were millions of stars. Holm 15a's depleted core is so large that it could encompass our entire Milky Way several times over. The structure of the galaxy around it is equally impressive. Holm 15a spans hundreds of thousands of light years, perhaps even 1 million, depending on how you define its faint edges. The outer regions blend gradually into the intra-cluster light, the diffuse glow made of stars that no longer belong to any single galaxy, but drift freely through the cluster. This faint ocean of orphaned starlight surrounds Holm 15a like a ghostly halo, and within that halo are the remnants of galaxies long since absorbed. Every faint star out there is a clue to a past collision, a reminder that this one galaxy is the product of countless others. The Abel 85 cluster itself is a gravitationally bound community of hundreds of galaxies, all orbiting a common centre of mass. These clusters are some of the largest structures in the universe that are held together by gravity. Within them, galaxies don't remain static. They move, they interact, and sometimes they collide. Over billions of years, those collisions produce the giant ellipticals that dominate the centre. Holm 15a sits right in that central position, the gravitational heart of the cluster, where the density of matter is highest. From that vantage, it slowly gathers material from its surroundings, drawing in gas, dust, and the occasional wandering galaxy. When scientists observed the stars in Holm 15a, they noticed that the stars in the outer regions move differently from those closer to the centre. The inner stars, what few remain, orbit under the influence of the central black hole's gravity, while the outer stars respond to the combined pull of the galaxy's mass and the larger cluster's field. This creates a delicate balance, a transition zone where the black hole's dominance fades into the collective gravity of the galaxy itself. Mapping those motions provides a glimpse into how such systems maintain stability. Even though the galaxy has endured countless mergers and disruptions, it has found equilibrium. The colour of Holm 15a's starlight tells another part of the story. The light is reddish, which means the stars are old. Blue stars burn quickly and die young, but redder stars are long-lived. The dominance of that colour indicates that Holm 15a has not formed many new stars for billions of years. The raw material for star formation, cold gas and dust, has mostly been used up or expelled during earlier mergers. When galaxies collide, the shock waves and gravitational forces trigger bursts of star formation, but eventually those bursts fade. The remaining gas either falls into the central black hole or is heated and blown out into intergalactic space. The result is a galaxy filled mostly with ancient stars glowing faintly, slowly aging together under the pull of their collective gravity. That quiet maturity gives Holm 15a a kind of cosmic stillness. In visible light, it's just a smooth, diffuse oval. No bright arms, no dark lanes of dust, no newborn stars twinkling in blue. Just the soft, even glow of billions of old suns. To some astronomers, that calm appearance is deceptive. Beneath it lies evidence of a violent history. Each faint ripple or irregularity in the light could be the lingering scar of a merger long past. The universe erases its own footprints slowly, but they're still there if you know how to look. When radio telescopes and X-ray observatories examine Holm 15a, they reveal something different. They show the traces of energetic activity near the centre, likely from matter heating as it falls toward the black hole. Jets of radio emission extend out from the core, faint but detectable, suggesting that the central engine is still active, though not as violently as in a young quasar. This is what astronomers call a low-luminosity active galactic nucleus, a black hole that is still feeding, but quietly. The accretion rate is modest compared to its size, yet even a small fraction of such immense energy produces measurable radiation across vast distances. It's remarkable that we can detect these faint signals at all. Each photon that arrives in a telescope is a survivor of a journey across intergalactic space, through clouds of gas, past magnetic fields, and through expanding space-time. By the time it reaches Earth, it's a whisper of its original self, stretched to longer wavelengths by the universe's expansion. But collected together, those whispers form a coherent picture, allowing scientists to reconstruct the structure of a galaxy hundreds of millions of light-years away. That's the quiet triumph of modern astronomy. It turns whispers into understanding. Holm 15a doesn't exist in isolation within the Abel 85 cluster. Around it are dozens of smaller galaxies, many of them moving slowly inward. Over the next few billion years, some of those will likely merge with Holm 15a, adding their stars and their own central black holes to its mass. The process never truly ends. On cosmic timescales, galaxies are fluid things, constantly changing. When we observe Holm 15a today, We're seeing just one frame in a much longer story, a snapshot of a system still evolving. From the centre of the cluster, the view would be extraordinary. If you could stand somewhere near Holm 15A and look up, though stand isn't really possible in space, you'd see the night sky filled not just with stars but with entire galaxies, glowing faintly against the blackness. Each one would appear much larger and brighter than galaxies do from Earth, because they're all so much closer together in the cluster's dense core. Some would show long tidal tails of stars stretching between them, the visible marks of gravitational interactions. It would be a sky filled not with constellations, but with islands of light adrift in the dark. The environment of a cluster like a Belle 85 is not empty. It's filled with hot, thin gas called the intracluster medium. This gas emits X-rays and forms a diffuse background that permeates the space between galaxies. The presence of that gas also affects how galaxies evolve. As a galaxy moves through it, the gas can strip away the galaxy's own interstellar medium, removing the fuel for star formation. Over time, that process turns once active spiral galaxies into passive ellipticals. Holm 15A, sitting at the cluster's centre, has likely absorbed much of this gas, its gravity pulling it inward to feed the central black hole. In many ways, Holm 15A is both a galaxy and a gravitational well, a region where the cluster's matter slowly accumulates. The boundaries between one and the other blur. The intracluster light merges into the galaxy's faint outer halo, and the galaxy's influence extends outward until it overlaps with the cluster itself. This is why the central galaxies of clusters are sometimes called CD galaxies, a term meaning they have extended envelopes that blend into their surroundings. Holm 15A is the archetype of such a system, vast, diffuse, and gravitationally dominant. Every detail of its structure tells us something about the past universe. The size of its core, the age of its stars, the faint trails of light around it. All of these are clues about how galaxies grow and evolve. The larger the core, the more mergers it must have undergone. The older the stars, the longer it has been since the last major influx of gas. The faint outer halo, full of stripped stars, tells us how violently those mergers occurred. It's like a forensic record, a slow-motion story of cosmic cannibalism spread out over billions of years. For astronomers, studying Holm 15A is like reading the universe's diary. It shows what happens when galaxies collide again and again, when gravity has enough time to smooth away the chaos and leave behind a single, enormous remnant. Inside that remnant, the central black hole waits, an accumulation of all the smaller black holes that once belonged to those lost galaxies. In that sense, Holm 15A is not just a galaxy. It's a community merged into one, its individuality dissolved into the collective mass of stars and dark matter that now share the same orbit around a single point of infinite density. The relationship between a galaxy and its central black hole is one of the most intriguing in astrophysics. Observations show a consistent correlation. The more massive the galaxy's central bulge, the more massive its black hole. It's as if they grow together, influencing one another through feedback mechanisms that balance their growth. When the black hole feeds too rapidly, it releases jets and radiation that push gas away, slowing down star formation. When it quiets, gas cools and stars can form again. Over time, this push and pull maintains an equilibrium, ensuring that galaxies and their black holes remain in proportion. Holm 15A fits this pattern, but at an extreme scale. Its black hole is immense because its host galaxy is immense. The two grew side by side, one shaping the other, until they reached a balance few others can match. The calm light we see now is the result of that balance. There are no major bursts of star formation, no violent outflows of gas, just quiet stability. In cosmic terms, Holm 15A has settled into middle age, its most tumultuous years behind it. Yet even now, its black hole may still be growing, slowly consuming any matter that drifts too close, adding infinitesimally to its already staggering mass. If there's a kind of poetry in this, it's not the romantic kind, but the mathematical one, the elegance of a system governed by simple laws that produce extraordinary results. Gravity, motion, light, all obeying the same equations everywhere in the universe. From the orbit of a planet around a star to the dance of galaxies around a cluster center, the rules are the same. Holm 15a is what happens when those rules play out on the grandest scale imaginable. Even so, there are limits to what we know. The deeper astronomers look into its core, the more questions arise. How exactly did the depleted core form? How many mergers did it take? Did each one leave behind traces we can still detect? Could there be something even larger than the 40 billion solar mass black hole we think we've found? Each new instrument, each new survey, pushes the boundary of what can be measured. With better resolution and deeper imaging, perhaps we'll refine the number, or even discover that Holm 15a's black hole is not alone, that it might one day merge again, producing a burst of gravitational waves strong enough to ripple through the universe itself. Until then, it remains a silent beacon of knowledge, a galaxy that hides its giant in plain sight. To the eye, it's just a patch of light in a telescope's field, another fuzzy oval in a sky full of them. But to those who look closer, who measure carefully and think deeply, it's a reminder that every glow in the night sky might conceal something beyond comprehension. Holm 15a shows that even in a universe as vast as ours, there are still extremes waiting quietly to be understood. When we talk about black holes, it's easy to forget that the word hole can be misleading. It suggests something empty, something that lacks substance. But what lies at the heart of Holm 15a is anything but nothing. It is mass, pure and unrelenting, compressed to an extent that defies our normal understanding of matter. What we call darkness here is not the absence of existence, but the weight of it. The kind of weight that bends space itself, that reshapes time, that turns gravity from a familiar tug into an all-consuming abyss. The weight of darkness is not metaphorical. It's measurable, calculable, written into the way light bends and the way stars move. It's the universe expressing its own density, and in Holm 15a, that density has been taken to an almost unimaginable extreme. In space, gravity is the sculptor. Every shape you see in the cosmos, from the curve of a planet's orbit to the spiral arms of a galaxy, is carved by gravity's patient hands. The black hole at the centre of Holm 15a is one of those hands made visible by its effects. It is gravity so concentrated that even the geometry of space curves around it. Physicists describe this using the language of Einstein's general relativity, where gravity is not a force pulling across distance, but a warping of space-time itself. Imagine laying a heavy ball on a stretched sheet of rubber. The ball makes a depression, and smaller marbles placed nearby roll toward it, not because they're pulled, but because the surface itself curves in that direction. Now imagine replacing that ball with something so dense that it doesn't just make a dent, it tears the fabric into a funnel. That's what a black hole is. Not an object sitting in space, but a region where space has folded inward beyond return. The weight of Holm 15a's black hole creates a curvature so extreme that within a certain distance all paths, even those of light, lead inward. This distance defines the event horizon, the boundary beyond which escape becomes impossible. For a 40 billion solar mass black hole, that horizon would stretch billions of kilometers across. It's a sphere of no return so vast that light, the fastest thing in the universe, cannot climb out once it crosses. And yet, paradoxically, outside that boundary, everything still behaves in ways we can predict and measure. Stars orbit it, gas flows toward it, space around it hums with the slow, steady rhythm of distorted gravity. Astronomers can't see inside the event horizon, but they can read the space around it like a map. The movement of stars near the core of Holm 15a, their accelerations, their velocities, all of that tells a story of the hidden mass. It's a story written in Doppler shifts, the tiny changes in colour that occur when light stretches or compresses as objects move. When a star moves toward us, its light shifts slightly bluer. When it moves away, it reddens. By measuring these shifts for thousands of stars, scientists can reconstruct the gravitational field that controls them. It's a kind of cosmic fingerprint, and Holm 15A's fingerprint shows something extraordinary. The gravity at its centre is so intense that no visible matter could produce it. Only a black hole of staggering size can explain the data. Gravity itself is simple in its nature, but infinite in its reach. It has no opposites, no shield. It's the weakest of the fundamental forces, yet because it only attracts and never cancels, it becomes the dominant force on the larger scales. It's what keeps planets in orbit, what binds galaxies, what shapes clusters like Abel 85. And it's what allows something like Holm 15A to exist. Every particle that has mass contributes to the curvature of space-time. Multiply that by billions upon billions of stars, merge them across cosmic time, and you begin to approach the magnitude of what sits in Holm 15A's core. It's not just a black hole, it's the sum of countless gravitational histories, a layered monument to every atom that ever fell inward. In physics, mass and energy are interchangeable. They are two sides of the same coin, connected by Einstein's famous equation E=mc2. It tells us that even a small amount of mass contains an enormous amount of energy, because the speed of light squared is such a vast number. A single gram of matter, if converted entirely into energy, would release as much as the explosion of thousands of tons of TNT. A black hole like Holm 15A's contains 40 billion solar masses worth of that energy, compressed into an invisible volume. Of course, not all of that energy is accessible. It's locked behind the event horizon, sealed by gravity's relentless inward curve. But the effects of that stored energy ripple outward across space. They dictate the motion of stars, the temperature of surrounding gas, even the alignment of nearby galaxies. What's remarkable is that black holes of different sizes affect their surroundings in different ways. Smaller black holes, like those formed by collapsing stars, can evaporate slowly through a process called Hawking radiation, a faint emission caused by quantum effects at the horizon. But for a black hole as massive as Holm 15A's, that radiation is effectively zero. Its lifetime is so long that it would take far longer than the age of the universe for it to lose any measurable mass. It's as close to eternal as anything we know. It simply sits there, massive, quiet, an anchor in the cosmic sea. Still, even something that's silent influences everything around it. When gas and dust fall toward the event horizon, they accelerate, heating up as they collide and compress. The temperatures in the accretion disk can reach millions of degrees, hot enough to emit X-rays and gamma rays. That light doesn't come from the black hole itself, but from the friction of matter just outside the boundary, energy released in the final moments before disappearance. If the black hole is feeding actively, it can outshine the entire galaxy around it. But Holm 15A's appears to be relatively calm now, perhaps in a resting phase. The light from its core is dim, suggesting that it's consuming very little at the moment. It has reached a kind of balance where the inflow of matter and the surrounding environment are in quiet coexistence. The idea of something so heavy yet so calm is fascinating. We're used to thinking of mass as something that crushes, something that causes chaos. But gravity on this scale isn't violent, it's steady. It pulls everything toward harmony. The orbits of stars near the centre settle into stable patterns, each one obeying the same fundamental equations that describe a planet orbiting a sun. The difference is just scale. For the stars of Holm 15A, the sun they orbit is invisible and 40 billion times heavier than our own. The forces are immense, but the motion is smooth. It's not destruction, it's structure. Scientists sometimes refer to black holes as natural laboratories for studying gravity, because they push the theory to its limits. In normal conditions, general relativity and quantum mechanics coexist peacefully, each describing different domains. But inside a black hole, where densities reach infinity and space-time curvature becomes absolute, the two theories collide. We don't yet have a unified description of what happens there. The equations break down, giving nonsensical results. That's what physicists mean when they talk about a singularity, not a physical point in space, but a place where our mathematics stops working. Holm 15A's singularity, if we could describe it, would be a region of near-infinite density, surrounded by an event horizon that hides it from view. It's the most extreme example of gravity we can imagine, and yet it obeys the same rules that govern everything else. To sense the scale of this, imagine standing somewhere far outside the galaxy, in the empty darkness of intergalactic space. From that distance, Holm 15A would appear as a faint smudge of light, barely visible even through powerful telescopes. Within that smudge, there are hundreds of billions of stars, each following predictable paths shaped by a gravitational center you cannot see. The entire galaxy moves as one, orbiting its own mass distribution, and yet, deep inside, at the very center, a black hole quietly holds everything in place. That's the paradox of weight in the cosmos. The heaviest things are often the quietest. When astronomers speak of the mass of Holm 15A's black hole, they do so with a kind of cautious awe. The methods used to measure it are indirect but precise. They rely on models that simulate how stars move under different gravitational potentials. By adjusting the parameters of those models until they match observations, scientists can infer the mass of the unseen object. It's a process that combines mathematics, physics, and careful observation. And even though there are uncertainties, perhaps 10 or 20% either way, the conclusion remains firm. This is one of the most massive black holes ever detected. The implications of that are profound. It suggests that there may be no upper limit to how large black holes can grow, at least not yet. It means that in the densest environments of the universe, where galaxies cluster and merge, gravity can create singularities of almost any size given enough time. It also raises questions about the early universe. If such giants exist now, how quickly did their seeds form? Did they begin as the remnants of the first stars, or did they collapse directly from primordial gas clouds before the first galaxies even appeared? The answers could reshape our understanding of cosmic evolution. And yet, for all the complexity of these questions, the essence of a black hole is simple. It is mass and it is gravity. The two are inseparable. The weight of darkness in Holm 15A is not mystical. It's physical, measurable, a direct consequence of the laws of nature. It's what happens when enough matter gathers in one place, when the pull inward becomes stronger than any other force trying to resist. The equations are the same ones that describe a falling apple, just scaled up to galactic proportions. That simplicity is part of what makes it beautiful. If you could watch Holm 15A over millions of years, you'd see that weight in motion. Occasionally a star would wander too close, drawn from the galaxy's outskirts toward the central void. As it neared the event horizon, tidal forces would stretch it into a long, thin stream of gas, a process called spaghettification. The material would spiral inward, heating and glowing before vanishing. For a brief time, the galaxy's core would flare, brighter than all its stars combined, before fading again into quiet. Each of those events is a reminder that even in the slowest parts of the universe, gravity never stops working. It's always pulling, always reshaping, always balancing the equation of mass and motion. There's something comforting about that constancy. No matter how strange the universe becomes at its extremes, the same rules hold everywhere. The same gravity that keeps you anchored to your bed right now is the same gravity that binds galaxies and curves light around black holes. It's a connection that runs from the smallest moment to the largest scale. When you drop a stone and watch it fall, you're watching the same principle that governs the orbit of stars around Holm 15A's dark heart. That connection is part of what makes studying the cosmos so grounding. Even when we talk about unimaginable distances and incomprehensible masses, we're still dealing with familiar laws. They just play out on scales our minds aren't built to handle. But with patience, we can translate them into understanding. The numbers become relationships, the relationships become patterns, and the patterns become meaning. In that way, even a black hole, the ultimate symbol of mystery, becomes something we can grasp. Holm 15A reminds us that darkness itself has structure. The black hole is not chaos, it's order taken to an extreme. It's the inevitable outcome of gravity having too much mass to manage. And that weight, that immense invisible pressure at the galaxy's core, is not destructive in the way we usually think. It's the glue that holds the galaxy together, the centre around which everything else orbits. Without it, Holm 15A would unravel. In the vast quiet of space, weight is not felt as pressure or burden. It's felt as curvature, as motion, as the invisible geometry that determines where everything goes. The stars of Holm 15A, ancient and red, move in gentle arcs defined by that weight. The gas between them flows inward, slow and steady. The cluster itself, with all its galaxies, orbits around a centre that is partly defined by this single black hole. The weight of darkness, in that sense, is the architecture of the universe itself. When we talk about something as immense as the black hole in Holm 15A, the question that often arises is simple but profound. How do we know? How can we measure something that cannot be seen, that lets no light escape, that hides behind its own gravity? It's easy to accept a number like 40 billion solar masses as a fact, but behind that number lies an entire world of observation, mathematics, and patient analysis. Measuring something invisible might sound like magic, but it's really the art of inference, the science of tracing what light does when faced with darkness. Astronomers don't need to see a black hole directly to understand it. They just need to watch how everything else behaves around it. Every measurement begins with light. Light is the messenger of the universe, the one thing that crosses the vastness between galaxies to bring us information. It carries with it details about its source, its energy, its colour, its movement. When light reaches us from Holm 15A, it has travelled 700 million years through space. It has been stretched by the expansion of the universe, bent by gravity, and scattered by gas and dust along the way. Yet still, enough of it arrives for our instruments to read its story. Within that faint signal lies the imprint of stars, gas, and the gravity that binds them. Astronomers use a technique called spectroscopy to decode that story. When light from a galaxy passes through a prism or a diffraction grating, it spreads out into a spectrum, a rainbow of colours with fine dark lines crossing it. Those lines are absorption features caused by atoms and molecules in stars and gas clouds absorbing specific wavelengths of light. Each element leaves a unique fingerprint, so by examining these patterns, scientists can tell what the galaxy is made of. But more than that, they can tell how the light has shifted. If the lines are displaced toward the red end of the spectrum, the object is moving away. If they're shifted toward the blue, it's moving toward us. These tiny shifts reveal motion, and motion reveals gravity. In Holm 15A, the stars near the centre move so fast that their spectral lines are broadened and blurred. It's as if their light has been stretched by the sheer speed of their orbits. By measuring the degree of that broadening, astronomers can determine the average velocity of stars in the region. The faster they move, the stronger the gravitational pull must be. From there, they can calculate how much mass is required to hold them in orbit. It's a process that relies on Newton's laws as much as Einstein's. The same principles that describe the motion of planets around the Sun can be applied to stars around a galactic core, just with different scales. But Holm 15A's case pushed the limits of what this method could handle. The velocities were so extreme, and the core so faint, that traditional optical data alone wasn't enough. The researchers turned to the Very Large Telescope in Chile, one of the most advanced optical observatories on Earth. Its instruments can collect light from distant galaxies with incredible precision, even from faint diffuse cores like that of Holm 15A. By pointing its adaptive optic systems toward the galaxy and stabilizing the image against the distortions of Earth's atmosphere, they could resolve the faint glow of stars near the center. Then, using an integral field spectrograph, they divided the image into thousands of small zones, each one producing its own spectrum. This allowed them to map the motions of stars across the core in 2 dimensions, building a velocity field, a detailed picture of how the stars move in every direction. Once they had that map, the next step was modelling. The scientists constructed computer simulations that described different possible mass distributions, some with smaller black holes, some with larger ones, and tested each model against the observed motions. The goal was to find the model that matched reality most closely. The model that required a black hole of around 40 billion solar masses produced the best fit. Anything less couldn't account for the high velocities and the shape of the galaxy's core. That's how they arrived at the estimate that stunned the astronomical community. Measuring something that far away is not a single observation. It's the accumulation of decades of techniques, refined through trial and error, verified against nearer galaxies where direct imaging is possible. For example, in the Milky Way, we can track individual stars orbiting Sagittarius A, the central black hole, and measure its mass directly from those orbits. By comparing those direct measurements with the indirect ones from galaxies like Holm 15A, astronomers can calibrate their models, ensuring that the physics scales correctly across orders of magnitude. The equations hold true whether the black hole has 4 million solar masses or 40 billion. The patterns remain consistent. The relationship between velocity and mass, the way gravity shapes motion, the way light stretches under its influence. Even with those tools, though, there are limits. The deeper you look into a galaxy's core, the harder it becomes to separate the light of stars from the faint background glow. The further away the galaxy, the weaker the signal. Observing Holm 15A required long exposures, hours or even nights of collecting light, just to build up enough photons for a reliable spectrum. Each data point in that analysis represents patience on a human scale and persistence on a cosmic one. And when the numbers finally emerge, they are not guesses. They are the distilled result of millions of tiny measurements, each one recorded, calibrated, compared, and checked against known physics. Sometimes people ask why astronomers can be so confident about something they cannot see. The answer lies in consistency. Every independent line of evidence points to the same conclusion. The motions of stars, the distribution of light, the structure of the core, all of them agree on the same story. If there were another explanation, such as a cluster of unseen dark objects instead of a single black hole, it would produce a different pattern of motion, one that doesn't match what we observe. The elegance of physics is that it doesn't allow for coincidence. If the data fits, the model stands. Beyond spectroscopy, there are other ways to measure the unmeasurable. One of them is gravitational lensing, the bending of light as it passes near a massive object. In extreme cases, this can create multiple images of distant galaxies, stretched and distorted by the curvature of space. In Holm 15A's case, the effect is subtle, but detectable. The light from background galaxies passing near it is slightly bent, its path deflected by the galaxy's gravity. By measuring the amount of that deflection, scientists can estimate the total mass of the galaxy, including both visible matter and the invisible black hole at its center. When lensing measurements and stellar dynamics agree, confidence grows. Even radio telescopes play a part. Instruments that detect radio waves can map jets of energy emitted from near the black hole. The size and strength of those jets can also provide clues about the black hole's mass and spin. In Holm 15A, the jets are faint but present, indicating a massive object that still exerts influence on its surroundings. The combined data from optical, radio and X-ray observations forms a layered picture, each wavelength adding a piece to the puzzle. What's striking is how indirect all of this is, and yet how certain. It's like inferring the shape of a mountain by watching the flow of rivers that run from it, or guessing the presence of wind by the motion of leaves. The mountain itself remains unseen, but its influence is everywhere. Measuring a black hole is the same. The thing itself is invisible, but the evidence of its presence is written across everything nearby. When astronomers present their findings, they don't just offer numbers. They include margins of error, confidence intervals, and detailed explanations of how the data was analysed. These reports are scrutinised by other scientists, challenged, tested and refined. In the case of Holm 15A, multiple independent teams have looked at the data and reached similar conclusions. That repetition, that agreement, is the foundation of scientific certainty. It's not about one observation, it's about a chorus of results that all sing the same note. And even then, scientists remain cautious. They know that measurements improve with better instruments. The upcoming generation of telescopes, like the extremely large telescope, also in Chile, will have mirrors over 30 meters wide, capable of resolving details 10 times finer than current technology. When it turns its gaze toward Holm 15A, it will refine those numbers further, perhaps revealing structures we can only guess at now. It might even show evidence of how the black hole interacts with its environment on smaller scales, providing direct visual confirmation of processes we currently infer. For now we work with what light gives us, and what it gives is astonishing. Every photon that reaches Earth is a traveller that has crossed cosmic time to bring us information about a place we will never visit. Measuring the unmeasurable is about learning to listen to those travellers, to decode the faint messages they carry. It's about patience, curiosity, and trust in the laws of nature. The same equations that describe the orbit of a moon around a planet can describe the orbit of a star around a black hole, and that symmetry is part of the quiet wonder of the universe. It's also a reminder that science doesn't need to see everything to know that it's real. The universe speaks through patterns, and those patterns are enough. We can measure mass without touching it, detect motion without movement, and describe gravity without ever leaving our own small corner of space. That's the elegance of inference, the gentle power of understanding that grows from observation alone. If you think about it, the process mirrors the way we understand much of life. We infer emotion from expression, intent from action, presence from silence. We read meaning into what we cannot see directly. Measuring the unmeasurable in that sense is a deeply human act. It's curiosity given structure, imagination disciplined by evidence. Holm 15A just happens to be the grandest stage for that act we've yet found. The more precisely we measure, the more clearly we see the relationships that govern everything. Gravity, motion, energy, all of them interlinked, all of them scaling smoothly from atoms to galaxies. The black hole's pull is just one expression of that continuity. When astronomers calculate its mass, they're really measuring how deeply it curves the space around it, how much geometry bends under its influence. In a sense, they're not weighing an object, they're weighing the shape of reality itself. As data continues to accumulate, the measurements of Holm 15A will grow even more precise. Perhaps the final number will change slightly, maybe 30 billion solar masses, maybe 50. But the essence will remain, a black hole of extraordinary scale, one of the universe's most massive. Each refinement brings us closer to truth, but also to humility, because every measurement reminds us of what we still cannot touch or see. And as the instruments gather light night after night, and the data streams in from telescopes across the world, that unseen giant continues its silent existence. The stars keep orbiting. The photons keep travelling. The weight of darkness remains, waiting to be measured again and again, each time with a little more clarity. It's a quiet dance between the seen and the unseen, between what the universe hides and what we are clever enough to uncover. In the end, the act of measuring the unmeasurable isn't about conquering mystery. It's about living alongside it, about learning to find comfort in partial understanding. Holm 15a doesn't give up its secrets easily, but it gives enough to know that something extraordinary is there, shaping the galaxy, bending light, holding time still at its edge. And somewhere beyond the reach of our instruments, beyond even the best models, lies the part we can only imagine, the part that reminds us why we keep looking. When we think of galaxies, it's tempting to imagine them as quiet, isolated systems drifting peacefully through space, each one keeping to its own place in the cosmic web. But the universe doesn't work that way. Galaxies move through clusters and filaments, drawn toward one another by gravity, their motion slow on human timescales, but relentless over cosmic ones. They are not static, they are travellers, and sometimes their paths intersect. When that happens, when galaxies meet, they don't simply pass each other like ships in the night. They merge. They tear at one another, reshaping stars, gas and dust, blending together until only a single, larger galaxy remains. The story of Holm 15a is the story of those collisions repeated countless times, the gradual accumulation of mass through gravity's endless patience. If you could speed up time enough to watch a cluster like Able 85 over billions of years, you would see galaxies moving like slow tides around a common centre. Their motions would look graceful, like a ballet of light. But as they draw closer, the balance changes. Their mutual gravity begins to distort them, stretching them into long tidal tails of stars and gas. Spiral arms twist and elongate, bridges of light form between them, and entire regions of star formation ignite under the compression of colliding gas clouds. It's a spectacle of motion and creation that unfolds silently, too slowly for any living being to witness in full, but real nonetheless. When two galaxies merge, their stars don't actually collide in the way you might imagine. The distances between stars are so vast that direct collisions are rare. Instead, the stars pass through each other's gravitational fields, their orbits changing subtly as they feel the influence of the combined masses. The real violence happens in the gas and dust. Those components are less diffuse, and when they meet, they compress, heat, and collapse, triggering bursts of star formation. In the early stages of a merger, galaxies can blaze with new stars forming at hundreds of times the normal rate. For a while, they become something like cosmic fireworks, brilliant and chaotic, a sudden bloom of energy before the system settles again. But as the galaxies continue to merge, the chaos gives way to structure. Their central regions spiral inward, drawn together by the drag of gravitational interactions. Each galaxy's supermassive black hole, once content in its own core, begins to move toward the new shared centre. These black holes orbit one another for millions of years, gradually losing energy through the emission of gravitational waves. As their orbits shrink, they come closer and closer until finally they merge into one. That final moment releases more energy and gravitational waves than all the stars in the galaxy emit in light, yet it happens invisibly, detectable only as a ripple in space-time itself. What's left behind is a single, larger black hole, a new centre of gravity for the merged galaxy. Over cosmic history, this process is repeated countless times. Holm 15a is the product of that repetition. Each merger added mass to its stars, expanded its halo, and enlarged its black hole. Over billions of years, those collisions built the colossal elliptical galaxy we see today. Its smooth, featureless shape is the mark of that long history. Spiral arms are delicate structures. They don't survive repeated collisions. Each merger randomizes the orbits of stars, erasing ordered patterns and leaving behind a roughly spherical cloud. The smooth light of Holm 15A is the signature of this well-aged chaos, the quiet aftermath of aeons of motion. Astronomers have simulations that show how this happens. Using powerful computers, they model the physics of dark matter, gas, and gravity across vast regions of space. When they run these simulations, galaxies form naturally along filaments of dark matter, grow by accreting gas, and then merge with one another over time. When they let the simulation run for billions of years, they see structures that look remarkably like Able 85, clusters with central galaxies that dominate the scene. Those simulated central galaxies develop the same hollow cores and the same massive black holes that we observe in reality. It's one of the triumphs of cosmology that these virtual universes behave like the one we actually live in. Each collision leaves its own fingerprint on the merged system. Some leave faint shells or ripples in the light profile, remnants of tidal interactions. Others scatter streams of stars far into the outer halo. Even when those features fade over time, the evidence remains in the galaxy's shape, in the distribution of its stars, in the mass of its black hole. Holm 15A's vast depleted core, the faint halo surrounding it, and the enormous black hole at its centre are all evidence of repeated mergers. They are the fossils of collisions long past. In a way, when galaxies collide, they are not so much destroying each other as becoming something new. The process is both violent and creative. The old structures are torn apart, but in their place, a larger, more stable system forms. The same process that can trigger supernovae and starbursts also leads to the birth of long-lived, quiet galaxies like Holm 15A. On cosmic scales, destruction and creation are the same thing. For astronomers observing from Earth, mergers offer a glimpse into how galaxies grow over time. Some can be seen mid-collision, their forms distorted and intertwined. The antennae galaxies, for instance, show long tails of stars flung outward by tidal forces. Others, like Centaurus A, reveal dust lanes and warped disks that betray a merger in progress. Holm 15A shows the end state, where the motion has long since settled. The violence is over, and only the equilibrium remains. It's a glimpse of what happens after the universe has had time to smooth out the rough edges. The gravitational interactions during a merger are complex. The black holes at the centres of the colliding galaxies don't merge immediately. They spend millions of years orbiting one another at great distances, gradually losing energy through friction with surrounding gas and stars. As they draw closer, the loss of energy shifts to gravitational waves, ripples that propagate through space-time. Eventually, when they are close enough, those waves carry away the last bit of angular momentum, and the two black holes coalesce into one. The merger produces a brief but intense pulse of gravitational energy, distorting space-time across the universe. Though we can't detect events that far away yet with precision, the same kind of ripples have been detected from smaller black hole mergers by instruments like LIGO and Virgo. Holm 15A's black hole may be the descendant of many such mergers, each one leaving behind an invisible echo in the fabric of space. These collisions also help explain why the largest black holes grow so massive. Each merger adds not just the mass of another black hole, but also access to new reservoirs of gas and stars. During the most active phases, as the black hole feeds, it can release enormous amounts of energy in the form of radiation and jets. That energy, in turn, influences the surrounding galaxy, heating gas and regulating star formation. The relationship between black holes and their galaxies is a feedback loop. The galaxy feeds the black hole, and the black hole, by releasing energy, controls the pace of the galaxy's growth. Over many mergers, this feedback balances out, leading to the kind of stable systems we see today. Holm 15A's quiet state suggests it has long since reached that balance. It's humbling to realise that even something as enormous as a galaxy can be transient on cosmic timescales. The Milky Way itself is on a collision course with the Andromeda Galaxy. In about 4 billion years, the two will begin to merge, and over another few billion, they'll settle into a single elliptical galaxy not unlike Holm 15A. When that happens, the supermassive black holes at their centres will eventually meet, forming a larger one that anchors the new system. For future observers, if any remain to look, our night sky will be unrecognisable. The graceful spiral structure of the Milky Way will be gone, replaced by a smooth, glowing oval of old stars. It's a reminder that the processes shaping Holm 15a are not remote curiosities. They are our own future, written at a larger scale. During a merger, the appearance of a galaxy changes dramatically. Gas clouds collapse into new stars, dust lanes twist, and the overall shape elongates before settling. The resulting galaxy may shine brightly in infrared and X-ray light, as the central black holes feed on the infalling material. But as time passes, the energy dissipates, the gas is consumed, and the system quiets again. The galaxies in Abel 85 surrounding Holm 15a are at various stages of that process. Some still contain active star-forming regions, others are already quiescent, fading into the background glow of the cluster. Holm 15a represents the final phase, the mature product of countless earlier collisions. The dynamics of galaxy clusters make these interactions inevitable. Gravity pulls everything toward the centre, and the larger a galaxy becomes, the more it attracts. It's a self-reinforcing process. The central galaxy, being the most massive, exerts the strongest gravitational pull, drawing in smaller companions. Those companions add to its mass, making it even more dominant. Over billions of years, this runaway growth produces the giants we see at cluster centres. Holm 15a is one of the most extreme examples, a galaxy so large that its own structure blurs into the cluster around it. Astronomers can even trace the remnants of past mergers by studying the motions of stars in the outer halo. Some stars move in distinct streams, their paths tracing the shapes of long-ago collisions. These stellar streams are like fossils of gravitational encounters stretched across hundreds of thousands of light-years. In Holm 15a, the light is too faint to map individual stars, but models predict that similar streams must exist there, hidden in the diffuse glow. Each one is the residue of a smaller galaxy that fell into the larger one, its structure erased but its stars preserved as part of the whole. As galaxies merge, their dark matter halos also merge. Dark matter makes up most of a galaxy's mass, even though we can't see it. It's the invisible scaffold that holds the luminous matter in place. When halos combine, they deepen the gravitational potential well, allowing the new galaxy to hold onto more matter. The black hole at the centre benefits from this as well. The deeper the potential well, the more material can fall inward to feed it. Holm 15a's enormous black hole may owe its existence as much to the accumulation of dark matter as to the mergers of luminous galaxies. The scale of these processes is staggering. A single galactic merger can take billions of years from start to finish. Entire civilizations could rise and fall, while two galaxies slowly draw together across the void. Yet when we look at images of merging galaxies captured by telescopes, the frozen moment of interaction looks almost instantaneous. A snapshot of something that, in reality, unfolds at a pace too slow for minds like ours to grasp. That's one of the paradoxes of astronomy. We see everything as it was, not as it is, and everything we see is a moment within a process that spans more time than we can imagine. For Holm 15a, those processes are long complete, at least for now. The collisions that built it happened billions of years ago, their light only now reaching us. The galaxy we observe is a relic of an earlier universe, one in which galaxies were closer together and collisions more common. In that sense, studying Holm 15a is like looking into a time machine. It tells us not just about itself, but about the universe's past, about how structure forms and evolves, how gravity sculpts matter into the shapes we see today. What's remarkable is that, even after all those collisions, the galaxy remains coherent. Gravity, though it can cause chaos in the short term, creates order in the long term. The same interactions that tear galaxies apart also bind them together into something new. The universe has a way of turning disorder into structure, of using destruction as a means of creation. Holm 15a is one of the grandest expressions of that tendency, a monument to the creative power of gravity. When scientists simulate galaxy mergers, they often end up watching the same story unfold again and again. Two galaxies approach, distort, collide, and merge. The new system stabilizes, and at its heart, a larger black hole forms. The process is so consistent across different initial conditions that it suggests universality. Wherever galaxies exist in proximity, mergers will happen. Wherever mergers happen, black holes will grow, and wherever black holes grow, galaxies like Holm 15a will emerge. It's not chance. It's the natural progression of cosmic evolution. Do you think about this while lying under the night sky, aware that our own galaxy is part of the same long story, is to feel a connection that transcends time. The Milky Way will one day follow the same path, merging with Andromeda, feeding its black hole, transforming into something new. The stars that make up our constellations will be scattered, their patterns lost, but new structures will take their place. In a universe where gravity never stops working, endings are always beginnings in disguise. And somewhere in that vast continuity, far beyond our future and our past, galaxies continue to collide. Each encounter releases energy, reshapes matter, and deepens the gravitational wells that will one day host black holes even larger than Holm 15a's. In the stillness of deep space, where galaxies drift like glowing islands on a sea of darkness, clusters form the great archipelagos of the universe. They are collections of hundreds, sometimes thousands, of galaxies bound together by their shared gravity. Within them, the space between galaxies is not empty, but filled with faint gas, invisible particles, and the subtle hum of gravitational tension. Each cluster is a small universe of its own, a system of structure and balance. And at the centre of many of these clusters sits a single, enormous galaxy, the one that has pulled all the others toward it over billions of years. In the Abel 85 cluster, that central giant is Holm 15a. It doesn't just occupy the centre, it defines it. Clusters like Abel 85 are among the largest structures in the cosmos that are still held together by gravity. Anything larger, like the filaments and walls of galaxies that thread across the universe, are only loosely bound. Clusters, by contrast, are stable. They are the endpoints of gravitational collapse, regions where matter has fallen inward from the surrounding void, forming a dense hub of galaxies, gas, and dark matter. Abel 85, located roughly 700 million light-years away, is one such hub. It spans millions of light-years across, a sprawling collection of hundreds of galaxies held together by the invisible framework of dark matter. If you could see it all at once, it would look like a faint web of light, with Holm 15a glowing at its centre like the heart of some ancient organism. The concept of a galaxy cluster is both simple and profound. Gravity gathers galaxies, and the cluster's overall mass determines its shape and behaviour. Within the cluster, galaxies move along orbits determined by the collective gravitational field. They don't move randomly. Their motions are governed by the cluster's mass distribution, which is dominated not by visible matter, but by dark matter. Astronomers can't see this dark matter directly, but they can infer its presence from the way galaxies move and from how light from distant objects bends as it passes through the cluster. The bending of light, gravitational lensing, acts as a natural detector, showing that the majority of the cluster's mass is invisible. Holm 15a sits right at the centre of that invisible structure, occupying the deepest part of the gravitational well, where the density of dark matter is highest. That central position makes Holm 15a something like the gravitational anchor of Abel 85. Every other galaxy in the cluster moves in relation to it. Over time, smaller galaxies spiral inward, drawn by the combined pull of the cluster and Holm 15a's massive presence. As they fall in, they bring their stars, their gas, and sometimes their own black holes, all of which contribute to the slow growth of the central giant. This process is known as hierarchical assembly, the idea that large structures form by the merging of smaller ones. It's a fundamental principle of cosmology, and Holm 15a is one of its clearest examples. If you were to visualize the Abell 85 cluster, you'd see something intricate and layered. The galaxies are not evenly spaced. They gather in groups and subclusters, each one orbiting the cluster's center in long, elliptical paths. Between them lies the intracluster medium, a hot, thin gas that emits X-rays. This gas is not dense by earthly standards, just a few particles per cubic meter, but it fills the entire cluster. It's so hot, reaching tens of millions of degrees, that it glows in high-energy light. X-ray observatories like Chandra and XMM Newton have observed Abell 85's diffuse glow, revealing filaments of gas stretching between galaxies and showing how the entire structure holds together. The temperature and distribution of this gas tell scientists how much mass the cluster contains, because only gravity that's strong could keep such hot gas bound instead of letting it drift away into space. Holm 15a, sitting in the middle of this web, acts like a sink for everything around it. Its gravitational reach extends far beyond its visible edges, overlapping with the cluster's central dark matter halo. Every particle of gas, every star, every satellite galaxy that passes too close eventually feels that pull. Over billions of years, that pull has shaped the cluster's evolution. Smaller galaxies that stray near Holm 15a are gradually stripped of their outer stars, leaving behind only their dense cores, which are then absorbed. This process, known as galactic cannibalism, sounds dramatic, but it's just gravity doing its quiet work. In the cluster's center, time moves on a scale so vast that even violent events unfold like a slow tide. The position of Holm 15a also affects the temperature and distribution of the intracluster gas. As the central black hole releases energy through jets and outflows, it stirs and heats the surrounding gas. This feedback helps regulate the cluster's core, preventing it from cooling too quickly. Without that energy input, the gas might cool, condense, and form new stars. But in most clusters, this doesn't happen. Instead, the gas remains in a delicate balance, constantly heated by the activity of the central black hole. In Abell 85, X-ray observations show cavities and bubbles in the gas near Holm 15a, signs that outflows from its central black hole have carved structures in the surrounding medium. These bubbles rise through the gas like smoke rings, evidence of past outbursts. They remind astronomers that even a black hole that seems quiet in visible light can still shape its environment across millions of light years. There's a kind of hierarchy in clusters. The galaxies orbit the cluster center, the stars orbit within galaxies, and everything orbits the central black hole indirectly, through the gravitational field it helps define. It's an elegant nesting of motion, from the grand to the small. The same equations describe all of it, scaled up or down. Each level depends on the stability of the one below it, and Holm 15a's black hole sits at the very foundation. It's not an exaggeration to say that the stability of the cluster's heart owes itself, at least in part, to that singular point of gravity. To understand just how massive the cluster is, astronomers measure the speeds of its member galaxies. The faster they move, the deeper the gravitational well must be. In Abell 85, some galaxies move at thousands of kilometers per second relative to the cluster's center. That velocity dispersion translates into an estimated total mass for the cluster of over 100 trillion times the mass of the Sun. It's an almost incomprehensible number, but one that tells us how tightly gravity binds this region of space. Out of that enormous mass, Holm 15a holds a small but significant fraction, enough to dominate the core itself. Clusters like this are also laboratories for studying the universe's large-scale structure. They show how matter has gathered since the Big Bang. The first small fluctuations in density in the early universe grew over time, attracting more matter and forming the seeds of galaxies and clusters. By observing clusters at different distances, astronomers can trace that growth through time, seeing how structures like Abell 85 came to be. Holm 15A, as the cluster's brightest and most massive galaxy, represents the culmination of that long process. It's a snapshot of cosmic evolution, frozen in light that has been travelling toward us for hundreds of millions of years. If you were to stand at the notional centre of Abell 85, near Holm 15A, and look outward, the view would be extraordinary. The sky would not be dark in the way we know it. It would be filled with the glow of other galaxies, hundreds of them, scattered across every direction. Some would appear larger and brighter, others smaller and fainter depending on their distance and size. The space between them would shimmer with the faint X-ray glow of the intracluster medium. Occasionally you might see the faint arcs of gravitationally lensed background galaxies, distorted by the cluster's mass. It would be a landscape of light and gravity unlike anything we can experience from within the Milky Way. And yet, for all its scale, the cluster would feel still. The motion of galaxies, while enormous in energy, is too slow to perceive directly. To an observer within it, the positions of the galaxies would seem fixed, unchanged over a lifetime. It's one of the paradoxes of cosmic motion. Everything is moving at unimaginable speed, but on timescales so long that it appears frozen. Holm 15A's central location makes it the still point in that turning world, the one place in the cluster where gravity's pull balances in every direction. Clusters also evolve over time. They grow by accreting smaller groups of galaxies from the surrounding cosmic web. These infalling groups bring fresh material, and sometimes their arrival triggers new activity in the central galaxy. A shock wave passes through the cluster's gas, compressing it and changing its temperature. Astronomers can detect these disturbances in X-ray observations, seeing patterns of turbulence and motion in what might otherwise seem static. Abell 85 shows signs of such activity. The outer regions of the cluster have filamentary structures, streams of galaxies still falling inward. Holm 15A's quiet appearance hides the fact that its environment is constantly changing, even now as new material continues to flow toward it. The central black hole plays a subtle role in maintaining this balance. When it feeds, it releases jets that heat and move the surrounding gas, preventing runaway cooling. When it rests, the gas can settle and condense, setting the stage for future activity. This cycle can last for hundreds of millions of years. Over that time, the black hole acts like a thermostat for the cluster's core, regulating its temperature and structure. It's a feedback mechanism on a scale far beyond anything we experience directly, but the principle is familiar. Systems seek equilibrium, even when the forces at work are vast. Dark matter is the invisible skeleton that holds the cluster together. Though it cannot be seen, its distribution can be mapped through gravitational lensing and through the motions of galaxies. In Abell 85, the dark matter forms a smooth halo centered on Holm 15A, extending far beyond the visible cluster. This halo defines the cluster's shape and controls how galaxies move within it. Without dark matter, the cluster would not exist. Its visible components would scatter into space. The fact that clusters like Abell 85 are stable is one of the strongest pieces of evidence for dark matter's reality. Holm 15A, sitting at the bottom of that potential well, occupies the most privileged position in this cosmic architecture. There's something poetic in the way clusters form and organize themselves. They begin as small fluctuations in the early universe, regions just slightly denser than their surroundings. Over billions of years, those tiny differences grow under the influence of gravity, drawing in more matter and deepening the gravitational wells. The densest regions form galaxies. The densest galaxies form clusters. The densest clusters form superclusters. Each level builds upon the last and ever-growing hierarchy of structure. Holm 15A and the Abell 85 cluster that surrounds it are part of that great cosmic tapestry, a node in the web of the universe. For astronomers studying clusters, the data comes not just from visible light, but from across the electromagnetic spectrum. Optical telescopes show the distribution of galaxies. X-ray telescopes reveal the hot gas. Radio observatories detect the faint signals of jets and synchrotron radiation from black hole activity. By combining these data sets, scientists build a multi-layered view of the cluster. Each wavelength reveals something different, and together they form a complete picture of the cluster's anatomy. Abell 85's observations tell a consistent story of a mature system dominated by a massive central galaxy and an even more massive dark matter halo. The balance of energy in the cluster is delicate. The hot gas radiates energy into space, slowly cooling over time. Without an energy source to counteract that cooling, the gas would eventually condense into stars. But observations show that this doesn't happen as often as expected. The likely reason is feedback from Holm 15A's black hole. Even when it's not actively feeding, occasional bursts of activity inject enough energy into the surrounding gas to keep it warm. These outbursts may occur every few 100 million years, each one reshaping the cluster's core and maintaining the equilibrium that has persisted for eons. In the grand structure of the cosmos, clusters like Abell 85 are not rare, but each one is unique. The arrangement of its galaxies, the temperature of its gas, the size of its central black hole, all of these depend on its individual history. Holm 15A's extreme characteristics make Abell 85 stand out. It's a reminder that even in the large-scale order of the universe, diversity thrives. Each cluster is a story written in gravity and time, a story of matter falling inward and finding balance in the most unlikely places. And as we imagine that balance, the slow dance of galaxies, the faint hum of heated gas, the invisible pull of dark matter, it's clear that the heart of a cluster is not a static place. It's a living system, in motion even when it appears still, in equilibrium even as it changes. Holm 15A sits at the centre of that system, a quiet giant holding the cluster together, its gravity linking galaxies, gas and dark matter into one vast coherent whole. When we talk about the boundary of a black hole, it's easy to imagine a physical surface, something tangible that you might reach out and touch if you could somehow survive the trip. But there's no surface, no wall, no solid barrier waiting out there in the dark. What astronomers call the event horizon is something subtler and stranger, a point of no return, a region where gravity becomes so strong that the paths of all possible futures curve inward. Once something crosses that threshold, it can never come back, not even light itself. The event horizon isn't made of matter, it's made of geometry. It's the shape that space takes when gravity wins completely. For a small black hole, the event horizon might be no larger than a city. For the black hole at the centre of our galaxy, it's about the size of the orbit of Mercury. But for the one in Holm 15A, that horizon is vast beyond anything we can meaningfully compare. If you could somehow replace our Sun with Holm 15A's black hole, its event horizon would extend far past Pluto's orbit, reaching almost 20 times farther than the edge of the solar system as we know it. The entire architecture of our planetary neighbourhood would fit comfortably inside, swallowed not violently but silently, disappearing across a line that marks the edge of physics as we understand it. The diameter of that horizon would be measured in light days, not kilometres. Light, the fastest thing in existence, would take days just to travel around it once. To picture this is to step into a realm where ordinary intuition fails. Space near the horizon is so curved that directions lose their meaning. What we think of as down, or inward, no longer applies. Instead, every path leads toward the centre, not because something is pulling it, but because the structure of space-time itself bends that way. It's not like falling into a pit. It's like moving along the surface of a funnel, where the slope keeps steepening until all directions curve toward the same point. That curvature defines the black hole's personality, and for Holm 15A's, is a curvature that reshapes an entire region of its galaxy. If we could see it directly, the view would be breathtaking. Around the event horizon, matter drawn in by gravity doesn't fall straight inward. It swirls, forming an accretion disk, a thin, rotating ring of gas heated to millions of degrees as it spirals down. The friction and compression within that disk release enormous amounts of energy, often enough to outshine the rest of the galaxy. But in Holm 15A, the feeding seems slow. The black hole's disk is faint, perhaps because the surrounding gas is sparse or too hot to settle into the disk efficiently. Still, even a small amount of infalling matter produces radiation we can detect across light years. To sensitive X-ray telescopes, the core of Holm 15A glows faintly, a quiet ember marking the location of something that defies comprehension. The light that escapes from near the event horizon carries information about what happens just outside it. As photons struggle to climb away from the black hole's gravity, they lose energy, stretching into longer wavelengths. This is called gravitational redshift, and for a black hole as massive as Holm 15A's, the effect is extreme. To an observer far away, the light from near the horizon appears dimmer and redder, as if it's being swallowed even before it crosses the boundary. If you were somehow hovering safely nearby, an impossible situation, but one worth imagining, you'd see the sky above you distorted beyond recognition. Light from the rest of the universe would bend around the black hole, forming a bright circular ring known as the photon sphere, where light orbits the black hole multiple times before escaping. The horizon itself would appear black, perfectly absorbing, framed by this halo of distorted light. This idea of the photon sphere became more than theory in 2019, when the Event Horizon Telescope captured the first image of a black hole shadow, the one in the galaxy M87. That image, a glowing ring surrounding a dark center, confirmed decades of predictions. The same physics applies to Holm 15A's black hole, only on a far grander scale. If we could image it in the same way, the ring of light would span thousands of light years across from our vantage point, and its faint glow would be the last visible trace of matter before it vanished forever. The fact that we can predict that structure so precisely, even without direct observation, shows how deeply we understand the mathematics of gravity. Einstein's equations describe how mass and energy curve space-time, and in turn, how that curvature affects the motion of matter and light. In the simplest form of those equations, a black hole is defined entirely by its mass, its spin, and its charge. For most astrophysical black holes, charge is negligible, so what really matters are mass and spin. Holm 15A's black hole is almost certainly spinning, possibly near the maximum allowed rate. That spin drags space-time itself around, with it in a phenomenon known as frame dragging. Near the horizon, space doesn't just curve, it rotates. Anything nearby, including light, is forced to move in the direction of the spin. This creates a region called the ergosphere, just outside the event horizon, where nothing can remain still relative to distant space. Within the ergosphere, energy can be extracted from the black hole through processes that twist magnetic fields and launch relativistic jets into space. Those jets, when they exist, are visible across enormous distances. Even a small one from Holm 15A would stretch tens of thousands of light years, a thread of energy extending from the heart of darkness. What makes the event horizon so fascinating is that it marks a boundary not between space and space, but between knowable and unknowable. Beyond it, our equations stop being predictive. We can describe what happens up to the edge, but not beyond. Inside, time and space exchange roles. For an object falling in, the horizon is not a wall. It's simply a moment it passes without noticing. There's no flash, no barrier, no sudden change. The transition is smooth, but from the outside, time appears to slow as the object approaches the horizon. To a distant observer, it never quite crosses, instead seeming to freeze in place, its light red shifting endlessly into darkness. It's one of the most striking illusions in all of physics. What takes seconds for the falling object takes eternity for the observer watching from afar. For Holm 15A's black hole, that time dilation is immense. If you could watch a star falling toward it, the light from that star would grow redder and fainter until it disappeared entirely, fading into invisibility. The star itself would be gone, but its final photons would stretch into the background, a ghostly afterimage marking its descent. To the black hole, that process takes no time at all. To us, it takes forever. This is the strange reality of relativity, where time depends on where you are and how fast you're moving, where gravity doesn't just shape space but also dictates the flow of moments. The scale of Holm 15A's horizon challenges not just observation but imagination. Even the largest numbers we use to describe it feel inadequate when scientists calculate its Schwarzschild radius, the radius of the event horizon for a non-rotating black hole. They get roughly 790 astronomical units. That's nearly a light we could cross. In other words, light, the universe's ultimate speed limit, would take about 7 days to travel from one side of the horizon to the other. For comparison, light takes just over 8 minutes to reach Earth from the Sun. We're talking about a boundary that dwarfs entire solar systems, a gravitational well deep enough to bend light across the scale of planets. And yet, despite that enormity from hundreds of millions of light years away, the black hole is invisible. It hides in plain sight, detectable only through its influence. It's a strange paradox of nature. The larger a black hole becomes, the less dense it is on average. For Holm 15A, the density within its horizon is lower than water. Its mass is enormous, but its volume increases faster than its mass as it grows. This means that, while it bends space-time profoundly, the matter within it is spread out across an immense region. What we think of as crushing density only applies near smaller black holes. For the giants, the gravitational pull at the horizon is relatively gentle. If you could somehow hover near Holm 15A's event horizon, you wouldn't feel the tidal forces tearing you apart as you would near a stellar mass black hole. The gradient of gravity across your body would be small. The danger would not be the pull, but the inevitability, the impossibility of turning back once you cross the line. That inevitability gives the event horizon a philosophical weight, as well as a physical one. It's a boundary that divides what can be observed from what can only be inferred. In a sense, it mirrors our own limits of understanding. No matter how advanced our instruments become, no information can ever escape from inside, because to do so would require exceeding the speed of light. The horizon is not just a feature of a black hole, it's a feature of knowledge itself. There will always be a region beyond our reach, a space where the universe keeps its deepest secrets. The mathematics describing this is beautiful in its simplicity. In the equations of general relativity, the event horizon arises naturally from the geometry of a mass collapsing under its own gravity. It's not something we impose. It's something the universe creates when enough mass occupies a small enough region of space. For Holm 15A, that region is vast, but the principle is the same. The horizon marks the limit where escape velocity equals the speed of light. Beyond that, the concept of outside loses meaning. Astronomers sometimes speak of the event horizon as the ultimate one-way door. Once you cross, every path leads inward. But it's not destruction in the ordinary sense. The matter that falls in still exists, its energy still contributing to the black hole's mass, but it becomes inaccessible. The information describing that matter, its exact arrangement, its history, appears to be lost. This leads to one of the most famous puzzles in physics, the information paradox. According to quantum theory, information can never truly be destroyed, yet black holes seem to erase it. Reconciling that contradiction is one of the central challenges of modern theoretical physics. Some scientists believe that the information is somehow encoded on the event horizon itself, in a thin layer of quantum fluctuations. Others think it might be released slowly over unimaginable times through processes like Hawking radiation. For now, the answer remains uncertain, hidden behind the same horizon that hides everything else. Thinking about Holm 15a in these terms stretches the imagination to its limit. We can measure its mass, we can infer its size, we can even simulate how it distorts light, but what lies inside remains beyond us. The equations predict a singularity, a point where density becomes infinite and the known laws of physics break down. But many physicists suspect that something else happens there, something that our current theories can't yet describe. It might be that quantum gravity, a theory that unites general relativity and quantum mechanics, will one day reveal what really occurs inside. Until then, the centre of Holm 15a remains a mystery in the purest sense, something both real and unreachable. From a distance, though, its influence is clear. The event horizon defines the black hole's gravitational identity, shaping everything within reach. The stars orbiting Holm 15a's core follow paths determined by that hidden mass. The gas clouds that drift too close spiral inward, heating and glowing before they vanish. Even the cluster's structure reflects the black hole's presence. The event horizon may be invisible, but its signature is everywhere. It's a reminder that in the universe, boundaries often mark beginnings as much as endings. And as we think about that, the way light bends, the way time slows, the way space itself curves, the scale of it begins to feel almost gentle. The black hole isn't violent in its essence, it's simply gravity taken to its logical conclusion. It's the point where the universe's rules fold back on themselves. Holm 15a is an example of that folding made monumental, a structure so immense that even comprehension bends around it. And somewhere, just outside its horizon, photons still circle, carrying with them the last whispers of light from the matter that ventured too near. Those whispers, faint and redshifted, travel outward into space, crossing millions of light years, reaching us as data, as signals, as measurable traces. They allow us to reconstruct the story of something that cannot otherwise be seen. The event horizon may be beyond comprehension, but not beyond imagination. And imagination, when guided by evidence, becomes understanding. The horizon of Holm 15a stands as both a physical boundary and a metaphorical one, marking the edge of what we know and inviting us to wonder about what lies beyond. Every massive object in the universe leaves a trace of itself, even when light cannot show it directly. Gravity is not silent. It ripples, bends, and hums across the fabric of space-time, and though those vibrations are faint beyond words, they carry information. If you listen closely enough with the right instruments, the universe speaks through these distortions. The great black hole at the heart of Holm 15a may be invisible, but its existence echoes through the cluster around it. Not in sound that we could hear with our ears, but in changes, movements, and patterns that reveal its presence. To imagine those echoes, you have to think of space not as emptiness, but as a medium, something that can stretch and compress. When two massive objects move, they disturb that medium. When they accelerate, especially when they orbit or merge, they send waves through space-time itself. These are gravitational waves, ripples predicted by Einstein a century ago and confirmed by observation only recently. They travel outward at the speed of light, carrying with them the record of their source. They pass through everything, through stars, through planets, through us, altering distances by less than the width of an atom as they go. We can't feel them, but we can detect them. When astronomers first measured gravitational waves in 2015, they came from the merger of two black holes tens of times the mass of the Sun. Those were small compared to Holm 15a's, yet even those modest events released more energy in a fraction of a second than all the stars in the observable universe emit in light during the same time. Now imagine the gravitational waves produced when galaxies like those that formed Holm 15a merged billions of years ago. Each collision between supermassive black holes would have sent colossal ripples across the cosmos. Those waves are too low in frequency for our current detectors to hear, but they are there, moving through space like deep ocean swells that never end. The galaxy cluster Abell 85, where Holm 15a resides, may still carry those vibrations within its structure. Not as measurable displacements, the distances are too vast for that, but as patterns in how matter is distributed. The slow evolution of the cluster's shape, the subtle motion of its galaxies, and the temperature gradients in its hot gas all bear the fingerprints of past gravitational events. Each time a smaller galaxy fell into Holm 15a, each time its black hole joined with another, space-time rang like a bell, and though that ringing faded, it never entirely vanished. It became part of the background, part of the quiet texture of the universe itself. Even light can carry these echoes. When gas falls toward a black hole, it heats up and emits radiation across the spectrum. X-rays, ultraviolet, visible light, even radio waves. That radiation flickers and varies depending on how matter flows inward. For Holm 15a, these variations are faint, but they exist. Sensitive instruments can detect changes in brightness that occur as matter moves through the accretion disk, as magnetic fields twist and reconnect, as tiny jets flicker on and off. Each fluctuation tells a story about how gravity interacts with matter on the edge of the event horizon. These are not random signals. They follow rhythms, sometimes repeating, sometimes chaotic, but always meaningful. Astronomers have learned to translate those rhythms into understanding. They use techniques like power spectral analysis to study how light varies over time, identifying frequencies that correspond to specific physical processes. In smaller black holes, these oscillations can reveal the inner structure of the accretion disk or the spin of the black hole itself. For Holm 15a, the timescales are much longer. The same processes that happen in seconds around a stellar black hole might take months or years to unfold here, because everything scales with mass. The larger the black hole, the slower the dance. Observing those long, faint fluctuations requires patience, but they are there. The breathing of the black hole, so to speak, the slow pulse of gravity interacting with matter. These echoes also exist in radio waves. When charged particles spiral around magnetic field lines near the black hole, they emit synchrotron radiation, a distinctive signature that radio telescopes can detect. In Holm 15a, faint radio jets extend outward from the centre, traces of energy carried away by twisted magnetic fields. These jets may have been more powerful in the past, during periods when the black hole fed more actively. What remains now is the ghost of that activity, a relic of times when the galaxy's core blazed more brightly. The radio emission is an echo of those ancient outbursts, still visible millions of years later. Even the gas surrounding Holm 15a remembers those moments. X-ray observations show cavities and bubbles in the hot intracluster medium, sculpted by past jets from the central black hole. Each bubble is a fossil of an outburst, a memory etched in plasma. By measuring the size and temperature of these bubbles, astronomers can estimate how much energy the black hole released and when. It's a form of cosmic archaeology, reading the layers of activity preserved in the gas. The picture that emerges is one of cycles, long periods of quiet punctuated by episodes of intense energy release, like a heartbeat stretched over millions of years. These patterns are not unique to Holm 15a, but its scale amplifies them. The energies involved are greater, the distances longer, the time scales immense. What might be a flash in a smaller galaxy becomes a slow rolling wave here. The result is a kind of cosmic low-frequency hum, too deep and too long to perceive directly but always present. If you could somehow convert those changes into sound, compressing time so that millions of years passed in seconds, you'd hear a deep, resonant tone, rising and falling as the black hole stirred its surroundings. It wouldn't be music in any ordinary sense, but it would be structured, rhythmic, a record of motion written in gravity. There are other kinds of echoes too, theoretical ones, predicted by ideas that push the boundaries of physics. Some models suggest that the event horizon itself might not be a perfect absorber, that quantum effects could cause it to reflect tiny amounts of energy, creating faint echoes after gravitational wave events. These hypothetical signals, if ever detected, would provide clues about what happens at the edge of a black hole. They would tell us whether the event horizon is truly sharp or blurred by quantum processes. No one has yet found definitive evidence for such echoes, but instruments are getting more sensitive. In time, they might reveal whether space-time itself has texture at the smallest scales. For now, the echoes we can study are the ones written in light and motion. Holm 15A's core, though dim, is not completely silent. The black hole's slow feeding creates occasional flares, sudden increases in brightness that fade again. Each flare marks the moment when a clump of gas crosses a threshold, releasing energy as it falls inward. These events remind astronomers that even the calmest giants still move, still change, still interact with their environment. The balance between quiet and activity defines what we see. When we look at Holm 15A through different kinds of telescopes, we see layers of history. Optical light shows the old stars smooth and unchanging. Infrared reveals the faint warmth of dust heated by long-ago energy. X-rays show the hot gas, stirred by past outbursts. Radio waves trace the remains of ancient jets. Each wavelength is an echo, each telling a part of the same story. Together they form a timeline stretching back billions of years, all centered on a black hole that endures through it all. What's remarkable is how consistent the evidence is across all these scales. The velocities of stars, the temperature of gas, the faint jets, the cavities in the X-ray maps, all of them align with a single source of gravity at the center. That consistency is what turns faint echoes into certainty. Science thrives on patterns, and Holm 15A's echoes repeat the same theme: gravity organizing matter, energy flowing outward, equilibrium restored. Even in the dark, the order remains. Sometimes it helps to think of these echoes as memory, not in the human sense, but in the physical one. Every interaction leaves a mark. Gravity doesn't forget. The cluster around Holm 15A remembers every merger, every flare, every ripple that passed through it. The arrangement of galaxies, the flow of gas, the temperature gradients, they're all part of that memory. When we study them, we're reading history written not in ink or stone, but in space itself. There's also a kind of symmetry in how these echoes connect the smallest and largest scales. The gravitational waves produced by merging stellar black holes and the slow pulsations of a giant like Holm 15A follow the same mathematical laws. The frequencies differ, the durations change, but the patterns are the same. That universality is one of the most comforting truths in physics. The idea that the same rules apply everywhere, from subatomic particles to cosmic giants. The echoes of a collapsing star and the echoes of merging galaxies speak the same language. And within that language is a reminder that nothing in the universe ever truly disappears. Energy transforms, matter changes form, light bends and fades, but the information of what happened remains encoded in the structure of the cosmos. The black hole's gravity may hide it from our eyes, but the effects radiate outward forever. Holm 15A's existence influences not just its own cluster, but the paths of galaxies far beyond, through the subtle pull of its mass. Its echoes stretch across space and time, touching regions that will never know their source. If you imagine the universe as a great field of invisible strings, each connected by gravity, then Holm 15A is one of the deepest notes in that cosmic instrument. Every motion, every vibration resonates outward, blending with others to form the background hum of existence. We can't hear it directly, but it's always there, filling the silence with meaning. The instruments we build, telescopes, detectors, satellites, are ways of tuning into that hum, of translating it into forms we can understand. Each detection, each data point, is a small piece of a vast symphony that began long before us and will continue long after. When you think about those echoes, it's hard not to feel a sense of continuity. The light that reaches us from Holm 15A today left its galaxy before humanity existed, before Earth even looked the way it does now. Yet it arrives, carrying with it the story of motion and gravity, of energy and time. The black hole may be beyond reach, but its voice crosses the ages. It reminds us that even in silence, there is connection. The more astronomers study these faint signals, the clearer the picture becomes. Black holes are not the dead ends of the universe they were once thought to be. They are engines, regulators, organizers of structure. The echoes they produce are the universe's way of balancing itself, transferring energy from one form to another, maintaining the rhythm of creation and collapse. Holm 15A's black hole may be massive beyond imagination, but it participates in that same rhythm, its echoes blending with the rest into the quiet harmony of the cosmos. And in those harmonies, in the faint traces that remain after the light is gone, there's a message about persistence, that nothing, not even darkness, is ever truly empty. Every motion leaves a trail, every collapse leaves a resonance, every silence hides a vibration. The echoes of Holm 15A may never reach us as sound, but they reach us as understanding, as a sense that the universe is not a static void but a living fabric, alive with motion and memory. And from that sense of connection, it becomes natural to wonder what those echoes mean for the story of the universe itself. If Holm 15A's gravity has shaped its cluster and sent waves through space-time, what does that say about the role of black holes in shaping the cosmos as a whole? What does this slow, silent gravity teach us about the balance between creation and collapse, between energy and emptiness? The universe, for all its apparent calm, has always been a place of hunger. Every star that shines, every galaxy that forms, every black hole that grows is part of a long chain of consumption and transformation. Matter falls inward, energy radiates outward, and in that endless exchange, structures emerge. The history of black holes is the history of appetite written across cosmic time, the story of how gravity, given enough patience, gathers what light disperses. Holm 15A's black hole is one of the grandest expressions of that process, the product of billions of years of quiet, relentless feeding. It all begins with collapse. In the early universe, long before galaxies took shape, clouds of gas and dark matter condensed under gravity. Within those clouds, the first stars ignited, massive, short-lived giants born from pristine hydrogen and helium. These were the first generation of stars, and many of them were enormous, hundreds of times the mass of the Sun. They lived quickly, burning through their fuel in just a few million years before dying in violent supernovae. Some left behind black holes, small by cosmic standards, but massive enough to serve as seeds. Others may have skipped the star stage entirely, collapsing directly into black holes tens of thousands of solar masses in size. Those early seeds mark the beginning of the universe's long experiment in gravitational growth. From that point onward, the process became one of accumulation. The first galaxies formed as these seeds drew in gas and merged with one another. Black holes grew as their host galaxies grew, each feeding the other in a feedback loop that spanned billions of years. When galaxies collided, their central black holes did too, adding their masses together. When gas fell inward, it heated and released energy, some of which escaped as light, the rest adding to the black hole's mass. The larger the black hole grew, the more efficiently it could feed, because its gravity reached farther. The result was a runaway process, limited only by the availability of fuel. The term astronomers use for this process is accretion. It's a simple word for a complex phenomenon. Accretion is what happens when matter falls toward a massive object and forms a disk around it. gradually spiraling inward as friction and magnetic forces transfer angular momentum outward. The energy released during accretion can be staggering. For every kilogram of matter that crosses the event horizon, about 10% of its mass is converted into radiation. That's far more efficient than any process known in chemistry or nuclear fusion. In a sense, black holes are nature's most efficient engines, turning matter into light and heat with near-perfect precision. For most of their lives, though, they are quiet engines. Feeding is not constant. It happens in bursts depending on the availability of matter. A black hole like Holm 15A's would have experienced long periods of near starvation, followed by sudden feasts as gas clouds or small galaxies wandered too close. Each episode would have lit up the galaxy's core, producing a quasar, a beacon visible across the universe. During the quasar era, about 10 billion years ago, the sky was filled with such lights. The centers of galaxies blazed as their black holes consumed matter at furious rates. Those luminous epochs were the times when black holes like Holm 15A's grew most rapidly. But feeding is never a simple process. As gas falls toward the black hole, the radiation it emits pushes outward, creating pressure that can halt further infall. This balance between gravity pulling in and radiation pushing out defines a limit known as the Eddington limit. When a black hole accretes near this limit, it shines at its maximum luminosity. Any more, and it would blow its own fuel away. For Holm 15A's black hole to have reached its current size, it must have spent long stretches of time accreting near that balance point, steadily converting matter into light and growth. Over billions of years, even modest feeding can build something immense. The evidence for these feeding cycles is written in the universe itself. Quasars seen in distant space are glimpses of the past, showing black holes in their youth, still consuming actively. As the universe aged and gas supplies dwindled, most black holes quieted. Their galaxies used up or expelled their remaining gas, leaving only hot, diffuse plasma that accretes slowly. Holm 15A's faint activity today is the echo of a long and busy history. The calm we see now is the calm that comes after appetite has been satisfied. Still, the traces remain. The enormous size of Holm 15A's depleted core suggests that its central black hole experienced multiple major feeding events. Each time two galaxies merged, their central black holes would have spiraled together, stirring the surrounding stars and gas. The final merger of the black holes would have released gravitational waves that carried energy away, allowing the new black hole to settle deeper into the core. The process would have cleared out the stars, creating the hollow center we observe today. The more massive the resulting black hole, the larger that hollow becomes. In Holm 15A, the hollow spans thousands of light years, a scar left by hunger on a galactic scale. Astronomers studying the growth of black holes often talk about the relationship between mass and time. A black hole can only double its mass every certain number of years if it accretes at the Eddington rate. For typical parameters, that doubling time is around 40 million years. Starting from a seed of 100,000 solar masses, it would take less than 1 billion years to reach 1 billion solar masses. To reach 40 billion, like Holm 15A's, it would take longer, but not impossibly so, especially if it began with a large seed or went through multiple mergers. The numbers fit within the universe's timeline. The black hole's existence is not an anomaly. It's a natural outcome of sustained appetite. There's also evidence that black holes grow in phases. Early on, they feed chaotically, swallowing whatever matter happens to come their way. Later, as galaxies evolve, the feeding becomes more organized, driven by inflows of gas along large-scale structures like cosmic filaments. These filaments act like rivers, channeling matter from intergalactic space toward clusters and their central galaxies. Holm 15A, at the heart of Abell 85, sits at the intersection of several such filaments. It's not just the center of a cluster, it's a crossroads in the cosmic web. Matter has been flowing toward it for billions of years, providing a steady supply of fuel. That constant inflow is what allowed its black hole to reach such extraordinary mass. Over time, this feeding changes not only the black hole, but also its host galaxy. The radiation and jets produced during accretion heat the surrounding gas, preventing it from cooling and forming new stars. This feedback regulates the galaxy's growth. Without it, galaxies would form too many stars too quickly, and then exhaust their gas entirely. Instead, the energy released by feeding black holes ensures that star formation slows and stabilizes. It's a self-regulating system, one that maintains balance between growth and quiescence. Holm 15A's quiet nature today is a direct result of that balance having been achieved long ago. To understand cosmic appetite fully, it helps to consider what happens to the matter that's consumed. Once it crosses the event horizon, it's lost to our universe, but its mass still contributes to the black hole's gravity. In that sense, nothing is truly wasted. The black hole doesn't destroy matter, it transforms it into curvature, into geometry. The energy released during accretion, meanwhile, radiates outward, heating gas, powering jets, and influencing the large-scale structure of the universe. The appetite of black holes drives cosmic evolution. Without it, galaxies would look very different, perhaps less stable, less ordered. In their hunger, black holes create the conditions for everything else to exist as it does. This connection between consumption and creation extends even to the earliest epochs of the universe. The first black holes may have helped trigger star formation by stirring the gas around them. The energy they released could have ionized the early universe, transforming it from opaque to transparent. In that way, the appetite of black holes helped light the cosmos. They are not just endpoints, they are engines of change. Holm 15A's black hole is a late chapter in that story, a mature example of a process that began more than 13 billion years ago. By now, it may have consumed everything within reach. Its growth has slowed to almost nothing, limited by the lack of cold gas in its environment. The surrounding cluster is hot and diffuse, making it difficult for matter to fall inward. The black hole will continue to grow, but only very slowly, perhaps by merging with other black holes in the distant future. For now, it waits in a state of quiet equilibrium, immense and stable. And yet, even in this apparent stillness, the process continues. The cluster around it evolves, galaxies drift closer, and over billions of years, new mergers will occur. Each one will bring fresh material and possibly new black holes to join with the central one. The history of cosmic appetite never truly ends. It just changes pace. The universe is patient. It works on timescales where waiting is as active as doing. When astronomers model the long-term future of the universe, they often predict that galaxies will continue merging until only a few enormous systems remain, each centered on a supermassive or ultramassive black hole. Eventually, even those galaxies will fade as their stars burn out. The black holes will remain, drifting through the darkened universe, occasionally meeting and merging. In the farthest imaginable future, trillions of years from now, those mergers will be among the last energetic events in existence. Gravity's appetite will be the final force still at work, long after everything else has gone quiet. There's something oddly comforting in that continuity. Black holes are often described as destroyers, but they are also preservers. They store the mass and energy of everything they consume, holding it within space-time's deepest wells. Holm 15A's black hole is not a devourer in the sense of waste. It's a collector, a keeper of history, containing within it the sum of countless stars, clouds, and smaller black holes. Its appetite has shaped its environment, but it has also stabilized it. The galaxy that surrounds it exists in part because of that gravitational hunger. The history of this process, stretching from the first stars to Holm 15A's immense core, is a story of the universe learning how to build complexity from simplicity. Gravity doesn't plan or design, it just follows its rules, and those rules inevitably lead to structure. From the smallest fluctuations in the early universe, from random differences in density, came galaxies, clusters, and eventually giants like Holm 15A. Its black hole is the endpoint of that long evolution, a monument to time itself, formed not by sudden creation, but by the accumulation of countless small events. When we observe it now, we're seeing the product of billions of years of cosmic appetite, refined by physics into balance. Its hunger continues, but at a whisper compared to the roaring quasars of the past. The same gravitational pull that once consumed galaxies now holds them steady in orbit, maintaining the order of the cluster. The same curvature that once drew in matter now defines the structure of space around it. The appetite has matured, transformed from a consuming fire into a quiet weight that keeps the cosmos coherent. And somewhere in that coherence, in the balance between feeding and stillness, lies a lesson about the universe itself. Growth is not always chaos, and hunger is not always destruction. Sometimes, the act of taking in, of drawing toward a centre creates stability. Holm 15A's history is proof of that. A history not just of what gravity consumes, but of what it creates through that consumption. Harmony, order, and the quiet endurance of form. There comes a point in every field of science where observation outpaces understanding. Something is seen that should not exist, or at least should not exist so easily given what is known. Holm 15A's black hole belongs to that category. It is so massive, so disproportionate to the galaxy that hosts it, that even in a universe filled with extremes, it feels like an overreach of nature. The problem is not that it exists, the evidence is strong, but that by current theories, it should have been much harder to make. Scientists call this the problem of being too big, a phrase that carries both humour and unease. In a universe governed by rules, Holm 15A's black hole seems to have skipped a few steps. When astronomers first estimated its mass, the number was almost uncomfortable to publish. Around 40 billion times the mass of the Sun, it was several times larger than the next confirmed black hole known at the time. The result forced a reconsideration of how such giants form. The basic models of black hole growth are well understood, through accretion of gas and mergers with other black holes, but there are limits. Even with steady feeding at the maximum allowed rate, it takes billions of years to reach masses like this. The early universe was not old enough to produce such giants through gradual means alone, yet we find evidence of them not just now, but also in quasars seen less than 1 billion years after the Big Bang. The pattern suggests that nature may have shortcuts, processes that allow black holes to grow faster or start larger than expected. To see why this is puzzling, it helps to look at the relationship between black holes and their galaxies. Observations show a strong correlation between the mass of a galaxy's central black hole and the mass of its stellar bulge. Typically, the black hole's mass is about 1,000th that of the bulge. This ratio holds across a vast range of galaxy types, suggesting that black holes and galaxies grow together. But Holm 15A breaks that rule. Its black hole is far too massive compared to its stars. Even accounting for measurement uncertainties, it outweighs what the relationship predicts by a large margin. It's as if the black hole kept eating long after the galaxy stopped growing. This imbalance raises questions about feedback, the process by which a feeding black hole regulates its own growth. When a black hole accretes matter, the radiation it releases can blow away or heat up the surrounding gas, preventing further accretion. This self-limiting mechanism keeps most black holes from growing uncontrollably. For Holm 15A's black hole to reach its size, that feedback must have failed, or at least been delayed. Perhaps the environment around it was unusually dense with gas, or perhaps the shape of the galaxy funneled material inward faster than radiation could push it away. Some researchers suggest that during a series of mergers, the usual checks and balances were disrupted, allowing short periods of runaway growth before equilibrium returned. Another possibility is that Holm 15A's black hole began larger than typical ones. In the early universe, dense regions of gas could have collapsed directly into massive black holes without forming stars first. These so-called direct collapse black holes could start out with masses of 100,000 or even 1 million suns, giving them a head start in growth. If Holm 15A's seed was exceptionally large, it would have needed fewer mergers and less accretion to reach its current size. In that sense, the problem of being too big might be a problem of being too old, a relic from a time when the rules of formation were slightly different, when conditions allowed for rapid growth that no longer happens today. The question becomes even more intriguing when you consider efficiency. Accretion is incredibly effective at converting matter into energy, but that efficiency comes at a cost. The more energy radiated away, the less mass actually reaches the black hole. For a rapidly spinning black hole, the efficiency can reach 40%, meaning nearly half the mass energy of infalling matter escapes as radiation. That radiation heats the surroundings and limits further feeding. For Holm 15A's black hole to have grown so large, its accretion might have been less efficient, slower, dimmer, but allowing more mass to fall in. It's a trade-off that could help explain its immense size and subdued luminosity. There's also the role of environment. Holm 15A sits at the centre of a massive galaxy cluster, surrounded by an ocean of gas and dark matter. The cluster's gravitational field funnels material inward over time. If Holm 15A has spent billions of years in that position, it has had access to a steady supply of matter. Even if the inflow is slow, the vast timescale makes up for it. A small but constant diet can build enormous mass if you wait long enough. In that sense, Holm 15A's black hole may simply be the product of perfect conditions. Plenty of time, abundant material, and a quiet environment that allowed uninterrupted feeding. Still, the numbers remain startling. The mass concentration required to produce such gravity is beyond ordinary comprehension. If we could somehow take the Sun and duplicate it 40 billion times, the resulting cluster would stretch across light years. Yet all of that is compressed within the event horizon of a single object, invisible except for the lighted effects. To the equations, it makes sense. To the human mind, it feels excessive. It challenges not just physics but perspective. The idea that something so vast could be so quiet, so complete in its invisibility. This too big problem also carries implications for cosmology. If black holes can reach such sizes, they may play a larger role in shaping galaxy clusters than previously thought. Their energy output during active phases could heat and redistribute the intracluster gas, influencing how stars form and how galaxies evolve. In extreme cases, a single ultramassive black hole could alter the balance of matter across millions of light years. Holm 15A's position at the cluster's centre suggests that it has done exactly that, acting as both anchor and architect for the surrounding structure. The existence of such giants forces theoretical physicists to refine their models. Some explore whether accretion physics might behave differently at high masses. Perhaps new instabilities or feedback mechanisms arise that we don't yet understand. Others question whether our current methods might underestimate the true number of massive black holes in the universe. Maybe Holm 15A isn't as rare as we think. Maybe we just haven't looked deeply enough into the most massive clusters to find its peers. Recent surveys with improved telescopes hint at this possibility. Several other galaxies have shown signs of similarly large central masses, though none confirmed to quite the same extent. If more are found, it would suggest that Holm 15A is not an outlier, but a clue to a broader pattern. There's also a philosophical side to the idea of being too big. It touches on the limits of growth, the point where natural processes reach their extremes. In stars, that limit is defined by balance between gravity and pressure. In galaxies, it's defined by the availability of matter and the cooling of gas. For black holes, the limit may be defined by time itself, by how long the universe has existed. Holm 15A may simply represent the frontier of what was possible within the universe's current age. If the cosmos were twice as old, perhaps even larger black holes would exist. The limit, then, is not a law, but a momentary condition, one that changes as the universe expands and evolves. Scientists often respond to anomalies like this with equal measures of skepticism and excitement. Skepticism because extraordinary claims demand extraordinary evidence, and excitement because anomalies are where progress begins. Holm 15A's black hole challenges the neat symmetry of existing theories, forcing us to ask whether our understanding of galactic evolution is complete. Each attempt to explain its size leads to new insights about how gravity, gas, and time interact. Even if the mystery remains unresolved, the process of trying to solve it enriches our understanding of everything else. In a more personal sense, there's something oddly reassuring about nature's capacity to surprise us. The fact that a black hole can grow so immense that it can quietly exist for billions of years, unseen until recently, reminds us that the universe is still larger than our imaginations. We can describe it, measure it, and predict it, but we cannot domesticate it. There will always be something that doesn't quite fit, something that stands at the edge of comprehension. Holm 15A's black hole sits on that edge, a reminder that knowledge expands only by confronting what doesn't make sense. The phrase "too big" implies a kind of judgment, as if the universe had gone overboard. But to the universe, there is no two. There is only what gravity allows, what time permits, what matter provides. The categories we use, small, large, normal, extreme, are conveniences of language. Nature does not recognize them. From gravity's perspective, Holm 15A's black hole is just another solution to the equations, a natural outcome of its environment. The discomfort lies not in the object itself, but in our limited sense of scale. And yet, that discomfort is useful. It drives curiosity, which in turn drives science. If every observation fit neatly into expectation, discovery would stagnate. The problem of being too big is really an invitation to look deeper, to refine models of accretion, to simulate mergers in greater detail, to build telescopes capable of seeing farther. Each new tool brings us closer to understanding, and each new anomaly broadens the horizon of what we consider possible. In the end, perhaps Holm 15A's black hole isn't too big at all. Perhaps it's exactly as it should be, the product of the universe's long patience and its capacity for accumulation. The question then shifts from how could it exist to how many more like it are waiting to be found. The history of astronomy suggests that whenever we think we've seen the limit, the universe offers something larger, fainter, or older just beyond reach. Holm 15A may only be the first whisper of a new scale of structure, one that redefines what galaxies and black holes can become. And as that realization settles, the idea of limits itself begins to soften. Maybe there are none in the absolute sense, only transitions from one range of possibility to another. What feels impossible today becomes ordinary tomorrow, as understanding catches up to observation. Holm 15A, with its immense, quiet black hole, stands as both puzzle and promise, a reminder that even in a universe governed by strict laws there is room for wonder. Darkness has always carried two meanings for us. One is the absence of light, the kind of darkness we close our eyes to avoid. The other is the presence of mystery, the space between what we know and what we have yet to learn. In that sense, black holes are the purest form of darkness imaginable, not just because they let no light escape, but because they represent the boundary of a knowledge itself. Holm 15A's immense black hole is one of the greatest examples of that boundary, a place where light, time, and matter are all bent into silence. Yet from that silence, we've learned some of the most profound truths about the universe. When we study darkness, what we really study are its effects on what remains visible. The stars that orbit Holm 15A's center, the gas that glows faintly as it spirals inward, the way light bends as it passes nearby, all of these are forms of communication. They show that even absence can have structure. A black hole doesn't shine, but it shapes everything that does. Its gravity dictates the architecture of the galaxy, the motions of stars, the temperature of the cluster's gas, even the paths of photons that wander too close. From the outside, the darkness is defined not by what it hides, but by what it reveals through its influence. This realization changes how we think about the universe. For centuries, light was the only messenger we trusted. Astronomy was built on photons, on measuring their brightness, their color, their position in the sky. But the study of black holes has taught us that gravity is a messenger too. It carries information not through illumination, but through motion. The curve of space itself tells a story, one that light alone cannot. Holm 15a, invisible at its core, still speaks through gravity, shaping the cluster like a silent conductor guiding an unseen orchestra. Darkness teaches us patience. It teaches that knowledge does not always arrive in brightness or clarity, but sometimes in inference, in quiet data, in subtle changes measured over years. The discovery of Holm 15a's black hole wasn't a single dramatic event. It was the result of long observation, of measuring light shifts and comparing models, of building confidence one equation at a time. In that sense, darkness rewards endurance. It asks for time, and it offers understanding only when we've learned to see without expecting direct illumination. It also teaches scale. When we confront something like Holm 15a's black hole, we're reminded of how vast the universe truly is. Numbers that look manageable on paper become incomprehensible when translated into human experience. The distances, the masses, the timescales, they all exceed our intuition. But in learning to accept those scales, we expand what our minds can hold. The universe trains our imagination by confronting it with enormity. We learn to think in millions and billions, to hold in our thoughts processes that take longer than life itself. That shift in scale is not just mathematical, it's philosophical. It teaches humility. Humility in science is not about smallness, but about openness. It's the recognition that every discovery expands the border between known and unknown, that answers create new questions. Black holes, by their very nature, are the embodiment of that dynamic. Every time we describe them more accurately, we also expose the limits of our theories. General relativity describes their geometry beautifully, but quantum mechanics insist that something more must happen inside. Between those two truths lies a gap we have yet to cross. Holm 15a stands there, a monument to that gap, a place where our best knowledge still stops short. Studying such darkness also changes how we think about order. We tend to associate darkness with chaos, with destruction or loss. But black holes are not chaotic. They're among the most orderly systems in existence. Their behavior follows precise mathematical laws. Given their mass and spin, their structure is completely defined. They are simplicity distilled. In that sense, they are not the universe's monsters, but its purest expressions of geometry. Holm 15a's black hole, enormous and silent, represents gravity reduced to its essence. Nothing extraneous, nothing disordered, only curvature and consequence. That order challenges the way we separate beauty from fear. For much of history, people imagine the heavens as places of light and perfection, and darkness as the realm of danger. But in physics, light and darkness are partners, each necessary to understand the other. Without darkness, light would have no context. Without light, darkness would be meaningless. The balance between them defines visibility itself. Holm 15a's black hole teaches that lesson on a cosmic scale, that even the most absolute darkness has structure, meaning, and purpose. Darkness also teaches proportion. The gravity that creates a black hole is the same gravity that keeps us grounded here on Earth. The only difference is scale. The equations don't change, they simply magnify. The same law that holds a teacup to a table also holds galaxies in orbit. Understanding that unity brings comfort, because it reveals that the universe isn't alien or separate from us. We live by the same rules that govern Holm 15a. Our lives are shaped by the same curvature of space-time, just in gentler forms. There's a subtle lesson too about perception. We tend to define reality by what we can see, But the study of black holes reminds us that the invisible can be more real than the visible. Most of the universe's mass is dark matter, dark energy, black holes. The luminous parts, the stars and nebulae we admire, are the exceptions. We exist in a universe where the unseen outweighs the seen. Holm 15A's black hole is a perfect metaphor for that truth. Invisible, yet essential, its gravity defining the structure of everything around it. The more we study such objects, the more we learn to trust inference, to believe in effects when causes remain unseen. That way of thinking changes how we approach not just science, but experience itself. The darkness also offers lessons about transformation. Everything that falls toward the black hole is changed. Matter becomes energy. Energy becomes curvature. Curvature becomes silence. Nothing is wasted. It's just rearranged beyond recognition. That process mirrors the transformations that occur everywhere in nature. The burning of stars, the decay of elements, the cycles of creation and dissolution. The black hole's darkness is not an endpoint. It's part of that cycle, a phase in the continual renewal of the universe. From its edges, new energy is released, influencing the birth of new stars elsewhere. Even the act of falling into a black hole radiates energy outward. Destruction and creation are intertwined. That balance between giving and taking, between light and darkness, reflects a kind of cosmic harmony. Holm 15A's black hole doesn't exist apart from its galaxy. It coexists with it, regulating its structure. When it feeds, it releases energy that prevents the galaxy from forming too many stars. When it rests, the gas cools and the cycle begins again. This feedback keeps the system in equilibrium. In a way, the darkness ensures stability. It restrains the excesses of light, maintaining balance in the cosmic ecosystem. There's a quiet poetry in that. The idea that the universe's deepest voids are also its stabilizers. On a more human level, studying such objects changes how we understand knowledge itself. It reminds us that not everything can be known directly, that mystery is not failure but fuel for discovery. The presence of something we cannot see invites the question, and the question sustains progress. Holm 15A's darkness is not an obstacle to understanding, it's an anchor for it. Around that anchor, science builds structure. The fact that we can measure its mass, predict its influence, and describe its geometry without ever seeing it directly is a triumph of reasoning. It shows that understanding doesn't require illumination, only connection. There's also the matter of perspective. From a distance, a black hole seems destructive, swallowing light and matter. But from the standpoint of physics, it's neutral. It doesn't prefer darkness to light. It simply curves space according to its mass. The meaning we assign, fear, fascination, beauty, comes from us. In that way, black holes are mirrors, reflecting our own interpretations back at us. They show us how we project emotion onto nature, how we translate vastness into feeling. Holm 15A's black hole doesn't brood or hunger or dominate. It just exists, obeying its equations perfectly. The drama we perceive belongs to us. Darkness also deepens our sense of continuity. The same physical principles that shape black holes govern everything else. When we study the darkness, we're not leaving the realm of the familiar, we're extending it. The same mathematics that describes a falling apple describes a falling star. The black hole is the logical endpoint of the same process that formed planets and moons. It's not an exception to the universe's rules. It's their fulfillment. That continuity is one of the great comforts of physics. It means that, however strange something appears, it still belongs to the same family of understanding. Holm 15A's black hole teaches another lesson, perhaps the most profound one, that comprehension and awe can coexist. We can describe the mathematics of its gravity, simulate the dynamics of its accretion disk, and still feel wonder. Knowledge does not erase mystery. It refines it. Each layer of understanding reveals deeper questions. What happens at the singularity? How does information survive, if at all? Is space-time continuous, or does it break into something discrete at that scale? These questions don't diminish what we know. They enrich it. Darkness, by withholding complete answers, keeps curiosity alive. If you think about it long enough, the act of studying black holes becomes a metaphor for the act of knowing anything deeply. We circle around what we cannot touch, measuring its influence, learning from its effects, inferring its nature. We move closer without ever crossing the horizon. That's not failure. That's the shape of understanding itself. Knowledge always has horizons, places where we must stop and imagine what lies beyond. Holm 15A's black hole simply makes that boundary visible. There's a quiet gratitude in this realization, a sense that the universe gives us puzzles not to frustrate us but to keep us reaching. Darkness teaches resilience. It reminds us that not all progress comes from clarity. Some comes from persistence in the face of the unknown. When we look into the dark, we're really looking at our own desire to understand. Holm 15A's gravity may shape space, but its mystery shapes thought. And perhaps that is the final lesson darkness offers, that it's not the opposite of light, but its partner in meaning. Without the unknown, discovery has no direction. Without silence, there's no contrast for sound. The black hole doesn't negate the universe's brightness, it defines it. By existing, it gives structure to what surrounds it, the same way night defines the stars. In that sense, Holm 15A is not a void but a context, a reminder that even in the absence of light, the universe is full of order, beauty and understanding waiting to emerge. The more we learn about the universe, the more it seems that every limit we draw eventually dissolves. The biggest star turns out not to be the biggest after all. The farthest galaxy soon gives way to one slightly farther. The oldest light is followed by a fainter, older glow. Holm 15A's black hole, once thought to stand at the top of that scale, may not be alone in its enormity. There are hints, whispers in data, and faint irregularities in distant light that suggest others might exist. Darker, heavier, perhaps even stranger. The question of whether there are bigger ones still waiting isn't just about scale. It's about the nature of cosmic growth, the balance of time and gravity, and the patterns that might repeat far beyond our reach. When astronomers confirmed the mass of Holm 15A's black hole, they knew immediately that it wouldn't be the end of the story. In science, singular examples are rarely final. The universe doesn't make one of anything. If such an enormous black hole can form once, the same processes that built it could have worked elsewhere, under similar conditions at other times. Clusters like Able 85 are not unique. There are thousands of galaxy clusters across the observable universe, each with a central galaxy of its own, each harbouring a black hole that has been feeding and merging for billions of years. Statistically, it seems improbable that Holm 15A's is the largest possible. It may simply be the first one we've measured in enough detail to realise just how massive these objects can become. The challenge, of course, lies in detection. The more massive a black hole grows, the more slowly it changes. Its accretion disk, if it has one, rotates on timescales too long for us to observe. Its light flickers less, its activity quiets, and its environment stabilizes. Paradoxically, the biggest black holes are often the most silent. They hide behind their own scale. Their gravitational influence is enormous, but spread over such distances that it blends into the galaxy's overall motion. Finding one requires extraordinary precision, measuring the speeds of stars and gas with instruments sensitive enough to detect differences of just a few kilometers per second, across millions of light years. Even with our best telescopes, that's near the edge of what we can do. Some candidates have begun to emerge. The galaxy IC Leather 1, for instance, located in the Abell 2029 cluster, has long been suspected of hosting a black hole rivaling or surpassing Holm 15A's. Its central region is vast, its light profile suggesting a core depleted by repeated mergers, the telltale sign of an ultramassive black hole at work. Estimates vary, but some calculations place its mass in the same range. Tens of billions of solar masses, perhaps more. Another contender, TON 618, an ancient quasar nearly 11 billion light-years away, shows an active core so bright that only a black hole of comparable or greater mass could power it. Its estimated mass, around 60 billion suns, makes it a strong candidate for the largest known. Yet the distance and the uncertainty inherent in modelling light from so far back in time means those numbers remain provisional. We know these giants exist, but we're only beginning to map their range. The search for the biggest black holes often begins not with images but with spectra, the way light from a galaxy or quasar spreads into colours. From that spread, astronomers can measure how fast gas is moving near the centre. The broader the emission lines, the higher the velocities, and the stronger the gravity that must be holding that gas in place. For active galaxies, this method is straightforward. The challenge is that not all black holes are active. Many, like Holm 15As, have already entered long periods of quiescence, consuming little and radiating even less. They reveal themselves only indirectly, through the slow motion of stars in their vicinity, or the shape of the galaxy's light distribution. Detecting them requires patience, as if listening for a heartbeat that beats once every 1,000 years. New telescopes are changing what's possible. Instruments like the extremely large telescope in Chile, with its 40-metre mirror, will be able to resolve the cause of distant galaxies with unprecedented detail. Space observatories designed to measure gravitational waves at low frequencies, such as the planned LISA mission, may one day detect the mergers of supermassive and ultramassive black holes directly, picking up the ripples that Holm 15A and others like it send across space-time. These detections would provide a new kind of map, not of light, but of gravity itself. Each signal would correspond to an event, each event to a black hole of a certain size, allowing astronomers to trace the hidden population that light alone cannot reveal. If larger black holes exist, they may reside in the most massive galaxy clusters, where matter has had time to collect for billions of years. In those environments, the conditions are right for growth without interruption. Abundant gas, frequent mergers, and a gravitational well deep enough to hold everything together. The central galaxies of these clusters, often called acidy galaxies, show extended envelopes of faint stars and enormous flattened cores, just like Holm 15A. Each of those cores could hide a black hole of similar or greater scale. What we see in Holm 15A might be the local example of a universal pattern. There's another possibility, more speculative but increasingly discussed, that some of the largest black holes might not be products of galaxies at all, but relics from the very early universe, primordial black holes that formed directly from density fluctuations moments after the Big Bang. If such objects existed and grew through mergers over time, they could have become the seeds of entire clusters, anchoring their formation from the start. It's an idea that blurs the line between cosmic structure and its cause. Instead of galaxies forming first and then producing black holes, perhaps black holes formed first and drew galaxies around them. If true, it would invert our understanding of how the universe organized itself. Holm 15A may offer clues about which picture is correct. Its black hole's mass is so disproportionate to its stars that it hints at an origin earlier than the galaxy itself. Perhaps its seed was already enormous before the first stars of Holm 15A's host ever shone. Over time, it may have grown alongside the galaxy, shaping it more than being shaped by it. If similar systems exist elsewhere, black holes whose host galaxies seem too small for their mass, it would support the idea that black holes were among the universe's earliest architects. The search for bigger ones, then, is not just about finding new extremes. It's about tracing the architecture of the cosmos back to its first blueprints. But even as these ideas unfold, there's a growing realization that bigger may not always mean rarer. Black holes grow naturally in environments that feed them, and the universe has had ample time to provide that nourishment. Some astronomers suggest that the distribution of black hole masses might follow a smooth curve, extending without a hard upper limit. If so, then Holm 15A's black hole isn't a singular outlier, but part of a continuum, one of many scattered across the vast web of clusters. We may have simply reached the observational edge of our current capabilities, mistaking the limits of detection for the limits of nature. The question of how big a black hole can become touches on deep aspects of physics. There are theoretical limits, though they depend on assumptions. A black hole cannot grow beyond the mass enclosed in its cosmic neighbourhood, because at some point it would consume or scatter everything available. It also can't accrete faster than radiation pressure allows, unless new mechanisms like mergers come into play. But these are practical constraints, not fundamental ones. The equations of general relativity place no upper bound on size. If enough matter gathers, the universe will permit its collapse. In that sense, largest is always a moving target. Time itself is the only true limiting factor. The universe, after all, is still young by its own standards. 13.5 billion years may seem like an eternity, but compared to its potential lifespan, it's barely a beginning. As galaxies continue to merge over the next trillions of years, black holes will keep growing. Clusters like Abell 85 will coalesce into even larger structures, and their central black holes will eventually merge as well. Far in the future, when starlight fades and galaxies settle into dark equilibrium, the universe may be ruled entirely by these giants. Their horizons will merge until only a few ultramassive black holes remain, scattered across a vast, dim cosmos. If time allows, there will always be bigger ones waiting. That projection feels both chilling and serene. It's not destruction in the usual sense, it's consolidation. The same way small streams join into rivers, and rivers flow into seas, black holes merge into larger holes. The process has no malice, only inevitability. Gravity collects what expansion leaves behind. Each merger erases individuality, but creates something enduring. Holm 15A's black hole, enormous as it is just a waypoint on that long path toward cosmic simplification. In the end, the universe may become a place of almost pure darkness, populated by horizons so vast that they barely curve space at all, their edges spanning light years, their centres indistinguishable from infinity. There's another kind of bigness to consider, not physical but conceptual. The discovery of ever larger black holes stretches our ideas about what reality can contain. It forces us to rethink the limits of observation, the meaning of time, and even the nature of information. If a black hole can encompass billions of suns, what happens to the complexity of everything that falls in? Does it vanish, or does it persist in some hidden form? Theories suggest that information may be preserved on the surface area of the horizon, encoded like data on an unimaginably vast sheet. If larger black holes exist, their surfaces would hold proportionally more information, perhaps making them the greatest repositories of order in the universe. What looks like emptiness could be the ultimate archive. That thought changes the emotional texture of darkness. Instead of emptiness, we begin to see fullness, the density of memory, the quiet containment of everything that ever fell inward. Holm 15A's black hole, then, is not just a void but a record, a physical embodiment of history. Larger ones, if they exist, would be even greater libraries of cosmic memory. The light they no longer release still echoes in the structure of their surroundings, in the distribution of galaxies and the rhythm of space-time itself. So are there bigger ones still waiting? Almost certainly. The universe has had no reason to stop making them. We just haven't found them yet. They may hide behind dust, behind distance, behind the limits of our current instruments. Or they may lie in plain sight, mistaken for something ordinary, because we haven't looked closely enough. Every decade of technological progress brings new clarity, and each time we refine our tools, the universe grows larger again. Holm 15A was once beyond imagination, then became a fact of measurement. Whatever comes next will follow that same path, from possibility to discovery to familiarity. And when we do find them, those larger black holes will likely teach us something subtle, not just about mass or size, but about patience. They will remind us that the universe doesn't hurry. It builds its extremes slowly, one collision, one orbit, one particle at a time. The bigger ones are not hidden because they are rare, but because they are timeless. They evolve on scales too slow for us to witness directly. Their growth is measured not in years, but in ages, their light delayed by distances beyond reckoning. To see them clearly, we must learn to think as the universe does, in spans of billions, not breaths. The question of what waits beyond Holm 15a is not just about the future of astronomy, but about our relationship with uncertainty. We know the darkness holds more than we can see, and that knowledge is enough. Whether the largest black holes are twice, 10 times, or 100 times greater, the essential lesson remains the same. The cosmos has no interest in boundaries. It unfolds endlessly into greater versions of itself. The idea that something bigger might still be out there is not a threat to understanding, but a continuation of it. And as that idea settles, it feels natural to turn from scale back to perspective, from what lies beyond to where it all belongs. Even the largest black holes, the most massive clusters, the grandest structures, exist within a universe that has no edge, no center, no final boundary. The search for what is biggest leads inevitably to the realization that everything is connected within that endless whole. The further we look into space, the less it seems to have an edge. Every direction leads to more galaxies, more stars, more light stretching outward until light itself begins to fade into the background glow of the early universe. There is no wall, no boundary where everything stops. The universe curves back on itself in ways our senses can't fully grasp. To stand beneath the night sky and imagine its shape is to face the purest form of infinity. Not an infinity of emptiness, but of continuation. Even something as colossal as Holm 15a's black hole is just a small event within that endless expanse. One structure among countless others, significant locally but vanishingly small against the whole. It's natural to wonder what edge even means in such a context. In daily life, we associate edges with endings, the place where something gives way to something else. But the universe doesn't behave like that. It has no outside. There is no surface you could cross to reach what's beyond. Space itself is all there is, and within it, distance and time are woven together so thoroughly that the concept of a boundary becomes meaningless. When cosmologists describe the universe, they often use the image of a sphere expanding, but it's not expanding into anything. The sphere is space itself. There's no exterior, only more interior unfolding in every direction. This idea can feel abstract until you begin to see the evidence. The cosmic microwave background, the faint radiation left over from the Big Bang, reaches us uniformly from every part of the sky. Its temperature varies by less than 1 part in 100,000, an astonishing level of smoothness. That uniformity tells us that, on the largest scales, the universe is the same everywhere. There are clusters and voids, galaxies and gaps, but averaged over vast distances it all evens out. There's no sign of an edge, no border where the pattern breaks. The universe repeats its structure endlessly, like a fabric with no hem, and yet, within that uniformity, there's immense variety. Each galaxy cluster is unique, each black hole the product of its own history. The combination of infinite continuation and local difference is what gives the cosmos its richness. The absence of edges doesn't mean sameness, it means connection. Every part influences every other, even if only faintly through gravity, radiation, or the subtle drift of expansion. Holm 15a, sitting quietly in a Bell 85, exerts its pull on the galaxies around it, which in turn tug on others, and those on still more distant ones. The chain extends outward without end. Even something as dense and isolated as a black hole is linked to everything else by the curvature of space-time. Nothing truly stands alone. Thinking about this can change how we see scale. The numbers we use in cosmology are so large they lose their emotional weight. Millions of light years, billions of years, trillions of stars, and they blur into abstraction. But the idea that space has no boundary brings a different kind of realization. It means that every point, no matter how far apart, participates in the same structure. Every light we see, every photon arriving at Earth, has travelled through this continuous expanse, untouched by edges, unblocked by walls. The night sky is not a window looking out. It's a cross-section of everything, an immersion in infinity. For scientists, the lack of edges isn't just philosophical, it's measurable. The way galaxies move, the redshift of their light, the rate of cosmic expansion, all of these point toward a universe that's finite in age but unbounded in shape. According to general relativity, space can curve back on itself without needing an outside. The simplest analogy is the surface of the Earth. It's finite, you can travel around it, but it has no edge. The universe might be like that, only in 3 dimensions instead of 2. Travel far enough in one direction, and in theory, you could end up back where you started, though the expansion of space makes that impossible in practice. The principle remains, there's no border to cross, only more space unfolding. This curvature has consequences for everything within it. Light doesn't travel in straight lines across infinite emptiness. It follows the contours of space-time shaped by gravity. On large scales, that curvature is gentle, but over billions of light years it adds up. The images of distant galaxies we see through telescopes are slightly distorted, stretched by the bending of space as their light passes through clusters and filaments. The result is a kind of cosmic mirage, revealing both the shape of the universe and the mass distribution within it. Even when we look at Holm 15a, what we see has been subtly altered by that curvature, its light bent, its position adjusted, its scale magnified by gravitational lensing along the way. In that sense, every observation we make carries the imprint of the universe's shape. There is no perfect straight line, no truly flat background. Everything we see is curved, not just locally by black holes, but globally by the geometry of all that exists. The universe without edges is not a void, it's a surface without boundary, dynamic and expanding. Its curvature too vast for us to notice except through the faint distortions it leaves in light. When we think of edges, we also think of endings. But in cosmology, even endings are relative. Stars die, galaxies fade, clusters merge, and yet the universe continues. The heat of one generation becomes the structure of the next. Even when the universe reaches its far future, when star formation ceases and black holes dominate, that too will not be an edge. It will be a new phase, a continuation of existence in a slower form. The universe may cool and darken, but it will not stop. Time itself stretches toward infinity, carrying within it the quiet persistence of gravity and space. Holm 15a's black hole fits into this continuity perfectly. It seems enormous when measured against a galaxy, but against the universe, it's a flicker. Its mass is a rounding error in the total energy content of the cosmos. Yet even that flicker has meaning. It shows how local processes, operating under simple rules, can build structures of staggering size. Gravity doesn't need to plan or coordinate. It simply acts, and given enough time, order emerges. The universe's lack of edges allows that order to repeat endlessly, forming galaxies, clusters, and black holes wherever conditions permit. There's no boundary to contain the process, no point where creation runs out of space. This absence of edges also redefines our idea of isolation. Nothing is truly separate in a universe that's continuous. Even the emptiest regions, the vast cosmic voids where few galaxies exist, are part of the same structure. Their emptiness is relative, a low-density patch in a pattern that extends forever. The same laws apply there as in the densest clusters. The gravitational influence of matter reaches across those voids, subtle but real. If you could somehow pause time and map every particle of matter, you'd find that all of it connects through an invisible network of forces. The universe is not a collection of things, it's a single, unbroken field of relationships. To grasp this, it helps to let go of the idea of edges as safety or containment. In human experience, boundaries provide comfort. Walls, borders, horizons. They define what's inside and what's outside. The cosmos offers no such comfort. It replaces edges with continuity, separation with relation. That can feel overwhelming at first, but it also opens a deeper sense of belonging. We're not on the edge of anything, we're within everything. Every atom in our bodies is connected through gravity and history to the rest of the universe. The iron in our blood, the calcium in our bones, the carbon in our cells all came from stars that lived and died in this edgeless space. The same physical laws that govern black holes govern us. The boundary between the cosmic and the personal dissolves. In a universe without edges, distance becomes a matter of perspective rather than separation. Light from the most remote galaxies we can see began its journey billions of years ago, yet it reaches us effortlessly, crossing the expanding fabric of space. Those galaxies are not out there in some inaccessible elsewhere, they are part of the same continuum we inhabit. The fact that their light reaches us proves that connection. When you look up at the night sky, you're not looking outward. You're looking through the universe's structure, along its curvature, seeing pieces of its own reflection. This realization also reframes how we think about time. Just as space has no edge, time may have no true beginning or end in the traditional sense. The Big Bang wasn't an explosion from a single point into empty space. It was the simultaneous expansion of space itself. Every region of the universe was once close to every other. The beginning happened everywhere at once. Likewise, the end, if there ever is one, will not occur at a single location, but everywhere simultaneously. The edge of time is like the edge of space, more a limit of perception than of existence, and in that context, even black holes take on new meaning. Their event horizons are edges locally, but not cosmically. They're boundaries within space, not of space. Beyond them, the universe continues. Their gravity curves space-time deeply, but only locally, a tiny fold in the fabric compared to the vast smoothness of the whole. Holm 15A's horizon might feel like an ultimate edge to anything that crosses it, but from the universe's perspective, it's a detail, a pattern within a larger pattern. The cosmos absorbs even its own boundaries, turning them into structure. Astronomers sometimes describe this property of the universe as self-similarity. On every scale, the same principles apply. Stars orbit galaxies the way planets orbit stars. Clusters gather like galaxies do, drawn together by the same equations. Even the larger structures, the filaments of dark matter connecting clusters across hundreds of millions of light years, resemble the neural networks of living brains or the veins of leaves. Patterns repeat, nested and infinite. In that repetition, the absence of edges becomes tangible. It's not an emptiness, but a rhythm, an architecture of connection that extends in every direction. This way of seeing the universe also changes how we think about our place within it. In an edgeless cosmos, there is no center. Every point is equally valid, equally within. That means Earth, tiny as it is, occupies the same status as any other place. We're not at the center, but neither are we at the edge. We're woven into the middle of everything, exactly where we must be. The light that reaches us from Holm 15A is not travelling from a distant exterior. It's moving within the same shared continuum. To study it is to study ourselves, not in the poetic sense, but in the literal one. The same physics that shape that distant cluster shapes our planet's orbit, our atmosphere, our own perception of time. The more we understand this, the quieter the universe seems. Its vastness stops feeling hostile and starts feeling steady. The lack of edges means there's nowhere to fall off, no boundary to fear. Everything flows into everything else, endlessly, gently, without interruption. Even entropy, the slow spreading of energies, is just another form of continuation. Over unimaginable timescales, heat becomes uniform, light stretches into longer wavelengths, motion slows, but nothing truly vanishes. Energy and matter transform, space expands, time flows on. The edgeless universe doesn't end, it diffuses. It's a comforting thought in its way. It means that the universe is not a stage set with limits, but a process with depth. Holm 15a, for all its enormity, is one expression of that process. A curve in space-time, a node in an infinite web, a local detail in a universal story. Its gravity connects to every other mass, its history to every other history. The light from its cluster mingles with the cosmic background, the same background that touches us here. Everything is part of the same conversation, and as that conversation continues, it becomes clear that the lack of edges is not just a feature of space, but a reflection of understanding itself. Knowledge, like the universe, has no final boundary. Each discovery opens a new horizon. Each answer expands the space of questions. Holm 15a teaches us this lesson in its own quiet way, by existing, by defying easy limits, by reminding us that even the greatest structures are parts of something larger. The absence of edges is not a void to fear, but an invitation to keep looking, to keep asking, to keep moving outward into the vast unending continuity that holds everything. And in that endlessness, after all the galaxies and horizons and distances, there is always a return, not to a boundary, but to perspective. The universe without edges still contains moments, places, and beings capable of wonder. The same infinity that allows Holm 15a to exist also allows consciousness to emerge here, on a small planet circling a modest star. Within that balance, everything belongs. There is a moment, after long contemplation of the infinite, when the vastness begins to feel familiar. What first seems overwhelming softens into something comprehensible, not because it has become smaller, but because we have grown a little closer to its rhythm. The mind adjusts to its scale. It no longer tries to hold the whole universe at once, but allows it to exist as it is, endless and continuous. The stars are still distant, the black holes still immense, but they no longer feel separate. They feel like extensions of the same reality we already inhabit. In that shift, the universe stops being a spectacle and becomes a home. After following the thread of Holm 15a across the dark, from its birth in collisions and collapses, to the unimaginable gravity at its heart, to the way its silence ripples through space, we arrive at a kind of stillness. There's nothing left to measure or prove here, only a recognition that we have been looking not at something foreign, but at another form of what we already are. The black hole at the centre of that galaxy is made from the same matter that made us. It's governed by the same physics, shaped by the same time. The difference is only in degree. Where we live our lives in seconds and years, it moves through eons. Where our gravity holds feet to the ground, its gravity holds galaxies. But it's all the same conversation between mass and motion, between energy and rest. That realization changes how the silence feels. It stops being empty. The darkness that fills the space between stars is not absence, it's potential. It's the structure that allows everything else to exist. Light travels through it, meaning is carried across it, and gravity weaves through it like invisible thread. Even when we look at the space between galaxies, we're not looking at nothing. We're looking at the medium that connects everything. Holm 15a's black hole, for all its density, is just one extreme of that same continuum. The fabric of the cosmos stretches unbroken from the smallest atom to the largest cluster. There is no gap between being and not being. There is only variation in form. The thought of that is oddly soothing. It means there are no missing pieces, no truly lost things. What falls into a black hole doesn't vanish from the universe. It changes its role within it. the matter that once shone as light becomes curvature, mass, the bending of space. The energy that escapes during that process travels outward forever, warming the gas of the cluster, stirring new motion elsewhere. Nothing is wasted. Nothing ends without giving rise to something else. The infinite is not an emptiness waiting to swallow meaning, but a process that keeps redistributing it. In a universe this continuous, even time feels less like a line and more like a tide. Every moment folds into the next, carrying traces of what came before. The light reaching us tonight from Holm 15A left its galaxy when our ancestors were still primitive mammals, when continents were in different places, when oceans covered lands that now rise above the sea. That light has crossed all of cosmic history to arrive here. It has passed through intergalactic gas, through expanding space, through gravitational lenses that bent it gently toward us. By the time it enters our eyes, it carries with it not only information about a distant galaxy, but a memory of everything it encountered along the way. In that sense, every photon is a message, not from somewhere else, but from the continuous whole that includes us. To sit quietly and imagine that is to feel a kind of belonging that has no borders. We are not observers looking out at a distant spectacle. We are participants, made of the same materials, moved by the same laws. The atoms in our breath were once part of stars. The gravity that holds our bodies together is the same gravity that holds galaxies in orbit. When we think about Holm 15A, we're not looking into something alien. We're looking into a mirror of the universe's own structure, a shape it takes when matter settles into its deepest form. The darkness of a black hole is not foreign to us. It's the other end of the same equation that makes light. And just as there are no edges in space, there are no true edges in thought. Curiosity moves in circles, returning always to its beginning. We start by asking what lies out there, and we end by realizing that out there and in here are parts of one continuous field of being. The laws that describe the motion of stars also describe the flow of blood, the stability of cells, the balance of tides. Scale changes, but the logic remains. The same simplicity that curves space around a black hole also shapes the orbit of a moon and the fall of a leaf. The difference is only magnitude. The continuity is absolute. When astronomers observe something like Holm 15A, what they really measure is not just distance or light, but coherence. The way all things hold together. Each equation that fits, each prediction that matches reality, is another sign of unity. Even the anomalies, the things that don't fit, point toward deeper order waiting to be understood. The problem of too big, the silence of the horizon, the echoes in the dark, all of them are invitations to see more clearly, not failures of understanding. The universe never contradicts itself. It only asks us to expand our sense of what's possible. This is perhaps the greatest comfort that science offers. It doesn't promise that the universe is easy to understand, only that it is understandable. The same patterns repeat, the same relationships hold, no matter how far we go. We can look 700 million light-years away to a black hole that outweighs galaxies, and still its behavior follows rules we can write down here, on this small planet, in our limited span of time. That is the quiet miracle of existence. That complexity is built from simplicity. That infinity is composed of rules elegant enough for us to grasp. And as we grasp them, something subtle happens. The infinite stops being an abstraction and becomes something intimate. The vastness of the cosmos, once a source of loneliness, begins to feel like connection. Every distant light, every gravitational curve, every whisper of radiation becomes part of a pattern that includes us. We are not at the edge of anything. We are in the center of everything we can know, and everything that can know itself. Even our awareness, fleeting as it is, seems to echo the universe's structure, a self-recognizing fragment of a self-organizing whole. Holm 15A's black hole, sitting quietly at the center of its galaxy, has no need to understand. It simply exists, following the equations that govern all matter. But we, tiny and temporary, have the privilege of reflection. We can look across light years and see our own physics at work, our own beginnings hidden in the same laws that bend starlight. We can feel awe and peace at once. We can recognize that we belong to something immeasurable and still find calm within that recognition. The darkness we once feared becomes an ally. It invites stillness, patience, acceptance. It teaches that meaning doesn't depend on visibility, that not everything valuable shines. The black hole's silence is not empty. It's the sound of equilibrium. Gravity has done its work perfectly. Matter has reached its most stable form. There is nothing left to fall, nothing left to resist. In that balance, there's a serenity that mirrors the stillness we seek in ourselves when thought finally rests. The cosmos, at its largest scale, and the mind, at its quietest, seem to share the same peace. As we imagine Holm 15a again, that vast galaxy adrift in the cluster's dim glow, its stars circling an invisible centre, it's easy to forget the numbers and just feel the shape of it. A glowing sphere of billions of stars orbiting in patient harmony. In the middle, a silence so deep that not even light escapes, and yet, somehow, everything depends on it. The gravity of that silence holds the structure together. Without it, the galaxy would drift apart. The stillness gives form to the motion. The invisible defines the visible. There's a lesson in that for everything, not just astronomy. The spaces between things give them their meaning. The quiet allows the sound to be heard. The pause gives thought its shape. Perhaps that is what the universe has been showing us all along, that infinity is not an expanse to be conquered, but a context to be felt. We can't measure our way to its end because there is none, but we can recognize its continuity. We can live within its rhythm. Every observation, every discovery, every moment of wonder is part of that rhythm. Even rest is part of it. Just as stars have lifetimes and galaxies have cycles, so do we. The universe doesn't hurry, and neither should we. If you imagine for a moment floating somewhere far above the plane of the Milky Way, looking back toward the faint glimmer of our galaxy among billions of others, and then beyond it to the Able 85 cluster, to the dim outline of Holm 15a glowing faintly against the background of cosmic night, what you would see is not isolation, but continuity. The same energy, the same physics, the same quiet motion repeated at every scale. The light would fade gradually, but it would never stop entirely. Even the darkest region between clusters would hold the faintest whisper of photons, the slowest hum of gravity, the subtlest trace of presence. And here, on Earth, that same universe continues in miniature. The night sky above us is the visible fraction of infinity, and our breathing, our thoughts, our calm attention are all part of it. The atoms in our eyes were once inside stars. The silence between our heartbeats is as real as the silence between galaxies. There is no separation between the vast and the small, only a difference in how we measure. The infinite doesn't live beyond us, it lives through us. So when we say goodbye to the infinite, it isn't really a farewell. It's an acknowledgement that the journey continues in every direction. That even as the story of Holm 15a fades into distance, its gravity still touches the rest of existence. Its light still travels, its influence still shapes the structure of space. And our understanding of it, however brief, becomes another link in that same chain of connection. The gentle goodbye, then, is not about leaving the universe behind. It's about returning to ourselves within it. It's about remembering that rest is part of discovery, that stillness is a way of listening. The universe, vast and silent, doesn't ask us to solve it. It only asks us to notice, to look, to wonder, to be here, within its unbroken continuity, for however long our time allows. And so, as the thoughts slow and the images of galaxies drift into the background, what remains is the quiet hum of gravity, the slow breathing of space expanding, the sense of belonging to something that has no edges and no end. Holm 15A, distant and immense, remains where it always has been, in balance, in motion, in silence. And we remain here, small but aware, resting in that same balance, part of the same infinite story, part of the same gentle, endless night,